Some nights the sky feels closer than it should. You lie still, and the dark above you doesn't press down, it opens, quietly, like a door left ajar in a house you've always known but never fully explored. And on those nights when the mind begins to let go of the day, there is something almost restful about looking up even from behind closed eyes and wondering what is actually out there. If this sounds like the kind of night you're having right now, you might like to stay a while. There's no rush here, nothing urgent, only a slow and gentle drift through something very, very large and very, very far away. Now, let's drift. There is a place in the universe so distant that the light traveling toward you from it has been moving continuously without rest for longer than the Earth has existed, longer than the Sun, longer than most of what we think of when we think of ancient things. It left its source before our solar system had taken shape, before the first oceans filled, before the first breath of any living thing on this planet. And it is still arriving. Right now, in this very moment, photons from that place are crossing the last quiet inches of space between the cosmos and the surface of a telescope somewhere on Earth. Scientists have given this place a name TON 618, though the name itself sounds more like a serial number than something deserving of awe. And yet, what it actually is something the human mind approaches slowly, carefully, the way you might approach the edge of something very deep. It is a black hole, not a small one, not the kind astronomers find scattered through galaxies like seeds a few times the mass of a star. This one is something researchers sometimes call ultramassive, a category that sits at the very far end of what the universe appears to have created. And even that word, ultramassive, doesn't quite reach it, doesn't quite hold the shape of what it means to be that large, that dense, that gravitationally complete. There is something almost calming about that, about a thing that exists beyond the reach of ordinary language. To find it in the sky, you would need to look toward a constellation called Canes Venatici, the hunting dogs, a quiet cluster of stars trailing behind the Great Bear in the northern sky. But even knowing where to look, you would never see TON 618 with your eyes. The distance is simply too great. The light has traveled so far for so long that by the time it reaches a sensitive instrument here, it carries only a faint signal, a whisper of energy encoded in wavelengths that scientists have learned to read. Researchers have found that the distance to this object is roughly 10.4 gigaparsecs. In more familiar terms, that translates to something in the range of 33 to 35 billion light-years, though astronomers are careful to explain that because the universe has been expanding the entire time that light was traveling, the true distance is not simply the travel time multiplied by the speed of light. Space itself was stretching. The destination was moving. And so what looks like a single fixed number is actually a description of a dynamic process, a relationship between movement and time that has been quietly unfolding since long before the Earth was formed. It seems that distance in cosmology is never just distance. It is also history. The light you receive from a star tells you what that star looked like when the light left it, not what it looks like now. This is true for every star you've ever seen on a clear night. The ones close enough to see with your eyes are showing you versions of themselves from years, decades, sometimes centuries ago. The more distant ones from thousands of years ago. And TON 618, at its extraordinary remove from us, is showing us something even further back. When that light departed its source, the universe was much younger than it is today. Scientists estimate that the cosmos is currently around 13.8 billion years old. The light we receive from TON 618 appears to have left when the universe was perhaps only a tenth or so of its current age, a period that cosmologists sometimes describe as a time of great turbulence and formation, when galaxies were assembling themselves from collisions and gas, when enormous structures were beginning to take shape in the dark. TON 618, or the quasar at its heart, was already operating then, already feeding, already pouring out energy at a scale that, if we could have been there to witness it, would have outshone everything else in its corner of the cosmos. Researchers have observed that quasars like this one extremely luminous galactic nuclei powered by actively feeding black holes were far more common in the early universe than they are now. The universe seems to have been in some sense more dramatic in its youth, more active, more bright, and now, billions of years later, most of that brightness has quieted. Those feeding black holes have largely grown still. They sit at the centers of galaxies, massive and silent, no longer consuming at the rates they once did. TON 618 may be among them now dormant, or nearly so. What we see from here is a memory, a record of something that burned long ago with unimaginable intensity. There is something in that which feels strangely peaceful. The mind scientists suggest has a particular way of responding to great distances. When we try to imagine something truly vast, not just large, but cosmologically large, the brain tends to shift into a quieter register. Researchers have observed that confronting scales far beyond normal experience often produces not anxiety, but a kind of soft suspension of ordinary thought. The analytical parts of the mind grow still. The part that measures and compares and categorizes finds nothing familiar to hold on to. And in that gap, something else moves in. Call it wonder if you like, or simply call it rest. There's a reason people have always looked at the sky when they needed to feel less crowded by the day. When the mind lifts its attention towards something incomprehensibly large, the small concerns, the conversations left unfinished, the tasks not yet completed, the quiet worries that trail us into evening, they don't disappear exactly. They just become very, very small by comparison. And small things are easier to set down. You don't have to think about TON 618 tonight. You don't have to understand it. It has existed without your knowing for the entirety of your life and long before that, and it will continue long after. There is nothing required of you here except to let the information arrive gently, the way light arrives after a very long journey quietly, without announcement. Somewhere right now, that light is still coming. It has been traveling since before the first tree grew on Earth, since before the first animal moved through shallow water, since before the continents found their current shape. It has crossed distances that have no name in ordinary language. It has passed through regions of space where there are no stars, no planets, no gas clouds, nothing but the quiet geometry of expanding spacetime. And it continues, patiently, in the way that only light and time and very old things can be patient. Scientists are still exploring what exactly lies at the heart of TON 618. They know its mass measured through the motion of gas, moving at extraordinary speeds around its edge through the particular way it bends and distorts the light behind it through a method called reverberation mapping, where the echoes of its own radiation tell a story about the depth and density of what it holds. The number that comes from these measurements is around 66 billion times the mass of our Sun. 66 billion suns, gathered into a single point of gravitational finality. It's a number the mind can read and still not feel. Not really, and that's all right. Some things are simply too large for feeling in the usual way. They require a different kind of reception, a quieter one, an openness rather than a grasp. Tonight, lying here, you are at an almost impossible distance from that object. 33 billion light-years, give or take, and yet something about it has reached you. Not the light itself, perhaps, but the idea, the quiet awareness that it is out there, that the universe contains somewhere in its dark geometry something of that scale. Researchers have found that simply engaging with ideas of cosmic scale, without pressure, without needing to fully understand, can gently ease the nervous system into a more receptive state. The mind, it seems, responds to enormity by releasing its hold on the immediate, by widening, by breathing out. And there is something else, something that scientists who study perception often note. When we follow a thread of curiosity slowly at night, without urgency or destination, the brain begins to settle into patterns associated with deep rest. Not because the information is boring, but because the pacing is gentle, because nothing is demanding, because the voice and the ideas are simply company moving softly through the dark alongside you. That is what this is. Company. Nothing more. There is a great deal more to understand about TON 618, about what it means for a region of space to be that dense, about what the boundary of a black hole actually is, about what happens to light, to time, to the very structure of space when mass reaches that scale. These things exist quietly at the edge of what we currently know, and there is something rather lovely about the fact that understanding them doesn't require urgency. They will still be there, those questions, waiting, as the light is still traveling, as the dark is still holding all of this in its usual patient way. And for now, that is enough. Light doesn't hurry. That might seem like an odd thing to say about something moving at nearly 300,000 kilometers per second, a speed so far beyond ordinary experience that no vehicle, no sound, no human thought has ever come close to matching it. And yet, measured against the distances of the universe, light is slow, patiently, steadily slow. It crosses the space between the Earth and the Moon in just over a second. It takes about 8 minutes to reach us from the Sun, and to travel from one edge of the Milky Way to the other, it would need to keep moving without pause for roughly 100,000 years. These are numbers that don't quite land the way numbers usually do. They pass through the mind and keep going like light itself, not stopping anywhere in particular, not attaching to anything familiar. And that, in a quiet way, is part of what makes them restful. Scientists describe light as electromagnetic radiation energy that moves in waves oscillating at frequencies the human eye can detect only within a very narrow band. What we call visible light, the warm gold of a lamp, the cool blue of a screen at night, occupies only a small slice of the full electromagnetic spectrum. Below it, in longer, slower waves, are radio waves and infrared. Above it, in shorter, more energetic forms, are ultraviolet light, and beyond that, X-rays and gamma rays, each carrying more energy, moving at the same speed, but vibrating at different rhythms. Everything we know about TON 618 has come to us through variations of this same phenomenon, through radio waves and X-ray emissions and the subtle bending of visible light, through instruments that can detect the faintest signals in the darkness and translate them slowly into information, into something approaching understanding. Researchers have found that this process of detecting distant light and interpreting what it means requires a kind of patience that mirrors something in the scientific temperament itself. You cannot rush the arrival of light from 33 billion light-years away. You can only prepare the instruments, open the aperture, and wait. There is something about that posture, the opened instrument, the patient waiting, that feels familiar at this hour. When the body is still and the room is dark, the senses widen. Small sounds become more present. The texture of the air changes. The mind, no longer occupied with the visible world, begins to register things it ordinarily filters out. Scientists suggest this is not simply imagination. Research indicates that in low light and quiet conditions, certain sensory systems actually become more sensitive. The threshold for detection lowers. The brain, no longer flooded with competing information, begins to notice subtler signals. In a way, you are doing what a telescope does. Right now. Opening. The speed of light was not always known. For most of human history, people assumed that light traveled instantaneously, that the moment a candle was lit, its glow arrived everywhere at once. The idea that light might take time to travel, that there might be a delay between its departure and arrival, was not seriously tested until the late part of the 17th century. A Danish astronomer named Ole Rømer noticed something unusual while observing the moons of Jupiter. The moon Io orbited its planet with reasonable predictability, but Rømer found that its eclipses, the moments when Io passed behind Jupiter, arrived slightly early when Earth was moving toward Jupiter and slightly late when Earth was moving away. The discrepancy was small, but it was consistent, and Rømer understood what it meant. Light was not instantaneous. It was crossing the varying distance between Jupiter and Earth, and that crossing took time. His estimate of the speed of light was not precise by modern standards. He calculated a value somewhat lower than what we now measure, but the reasoning was sound. He had caught light in the act of traveling, had clocked it imperfectly against the reliable rhythm of a moon. What strikes researchers who revisit this story is not the number Rømer arrived at, but the method. He didn't measure light directly. He measured its delay. He listened for what was slightly off, slightly early, slightly late, and from that irregularity, he inferred something fundamental about the nature of the universe. It seems that so much of what we know about distant things comes not from direct observation, but from careful attention to discrepancy, to the thing that doesn't quite fit. to the signal that arrives a fraction of a second off schedule carrying in its small deviation the answer to a very large question. There is a word in physics, redshift, that carries the same quiet logic. When an object in space moves away from us, the light it emits stretches. The waves become longer. In visible light, longer waves shift toward the red end of the spectrum, hence the name. And because the universe is expanding, because every distant galaxy is moving away from every other distant galaxy, the light from far-off objects is almost always redshifted. The further away something is, the more its light has stretched, and the greater the redshift astronomers measure when they examine it. TON 618 has one of the highest redshift values ever recorded for an object of its kind. When astronomers first began studying it in the middle of the 20th century, it was initially catalogued as a radio source, a distant point of electromagnetic noise. They measured its redshift and found that the light had stretched enormously during its journey. That stretching told them how far the light had traveled, which told them how far away the source was, which told them they were looking at something from the early universe, something billions of years old, something whose present state, if it has a present state in any meaningful sense, is entirely unknown to us. We are receiving a message from a past we cannot visit. And the message, encoded in stretched wavelengths and shifted frequencies, says something very large was here. Researchers have observed that there is something psychologically distinctive about receiving information across extreme delay. When we learn that the light from a distant star shows us that star as it was 1,000 years ago, the mind does something interesting. It doesn't just register a fact. It briefly holds two timelines simultaneously: the present moment here in this room and a past moment there, in a space so remote it has no experiential equivalent. The brain neuroscientists have noted handles this kind of temporal displacement with a particular kind of quiet. Not confusion, but a gentle suspension. A loosening of the ordinary sense that time moves in one direction, steadily, predictably, under control. At night, that loosening can feel like relief. There is also the question of what light carries with it beyond energy and frequency. Every photon, every tiny packet of light energy that arrives at a telescope from a distant source carries information about the conditions where it was created, the temperature of the gas it passed through, the magnetic fields it crossed, the density of the matter it navigated on its long transit. Scientists can read these signatures in the spectrum of arriving light, the way a careful reader might notice in a letter sent long ago, not just the words, but the quality of the paper, the pressure of the handwriting, the faint traces of wherever the letter was kept before it arrived. The light from TON 618 has passed through enormous structures, through galaxy clusters, through intergalactic gas, through regions of space where gravity bent its path slightly, where the geometry of space-time curved just enough to nudge it from a perfectly straight line. By the time it arrives at a detector on Earth, it has been shaped by everything it crossed, and scientists with careful analysis can begin to untangle some of those shapings, can read in the arriving signal the partial history of its journey. It may be that this is not so different from the way memory works. Research suggests that when we recall something, a place we've been, a person we once knew, a moment from long ago, the memory that surfaces is not a pure recording of the original event. It has been altered by everything that happened between then and now, by sleep and time and reinterpretation and the gradual gentle reshaping that all memories undergo simply by existing in a mind that keeps changing. We are, in a sense, always receiving light from a past that has already been altered by the crossing. None of this needs to be held tightly tonight. These ideas about light and speed and distance and the patient encoding of information in stretched wavelengths, they are the kind of ideas that settle better when they are not gripped, when they are simply allowed to move through the mind at their own pace, touching what they touch, releasing what they release. Scientists who study the relationship between cognitive state and information processing have found that the mind often integrates complex ideas more effectively during periods of low arousal, during the gentle, half-attentive state that comes before sleep, when the analytical structures are quieting and something more diffuse takes over. This is not a failure of attention. It is a different kind of attention, broader, less focused, more receptive to connection than to analysis. So if you find that some of this drifts past without fully landing, that is not something to correct. That is, in a sense, the point. The light has been traveling for billions of years to reach here. It does not require you to fully understand it, only to receive it in whatever quiet way you can. And somewhere in the far dark, beyond all the stretching and the redshifting and the long patient crossing of enormous space, there is still more to notice about what TON 618 actually is, about what kind of thing a black hole at that scale truly holds at its center, about what it means for something to be that dense, that final, that still. That understanding moves at its own pace, and it is already on its way. There are things the eye cannot find, and yet the mind knows are there. You have felt this before, probably. The presence of something in a room before you turn to look. The weight of a silence that is somehow different from an empty silence. The way certain places carry something, a quality, an atmosphere that cannot be pointed to directly, but is nonetheless unmistakably real. Scientists who study perception have spent considerable time trying to understand how the brain constructs presence from incomplete information, how it fills in what the senses cannot directly confirm, how knowing and seeing are in the end very different processes, and yet the mind moves between them so fluidly that the seam is almost invisible. This is, in a quiet way, the central challenge of understanding a black hole. You cannot see one, not directly, not in the way you see a star or a planet or even a distant galaxy as a soft smear of light in a long exposure photograph. A black hole, by its nature, does not emit light from its core. It does not reflect. It does not glow. What it does is shape. It shapes everything around it. And it is through that shaping, that bending and distorting and influencing, that we have come to know it exists at all. The term itself has a history worth lingering on. For a long time, the objects we now call black holes didn't have a name that quite fit. In the middle of the 20th century, physicists were working with mathematical descriptions of what should theoretically happen when enough mass collapsed into a small enough space. The equations of general relativity developed by Albert Einstein in the early part of that century, predicted the existence of regions where gravity became so extreme that nothing, not even light, moving at its full and extraordinary speed, could escape. These regions were sometimes called gravitationally collapsed objects, or frozen stars, or dark stars. None of these names stayed. Then, in the late 1960s, the American physicist John Wheeler began using a different phrase, black hole. Two words, simple and stark, that somehow captured something the longer technical names had missed. Not just the darkness, but the absence, the hole. The place where something used to be, or where something is, but where the usual rules of presence and visibility no longer apply. Wheeler was known for his gift with language for finding the phrase that made an idea feel inevitable. Researchers who have studied the history of physics often note that names matter more than they might seem. A good name shapes how a concept is held in the mind. It determines which questions feel natural to ask. Black hole, for all its simplicity, asks the right question: what happens to a place that cannot be seen? What happens, it turns out, is geometry. General relativity describes gravity not as a force pulling objects together, the way it was understood before Einstein, but as a curvature in the fabric of space-time. Mass creates that curvature. The greater the mass, the deeper and steeper the curve. An ordinary star like the Sun creates a gentle curve enough to keep the planets moving in their orbits, enough to bend passing light by a measurable but small amount. A more massive object creates a deeper curve, and a black hole creates something that physicists describe as a singularity, a point at which the curvature becomes, in the language of mathematics, infinite. Around that singularity, at a certain distance determined by the mass of the object, lies the event horizon. This is not a physical surface. There is no wall, there no membrane you could touch. It is a mathematical boundary, the point of no return. The distance from the center, at which the escape velocity, the speed required to pull free of the gravitational pull, reaches the speed of light. And since nothing with mass can reach the speed of light, and even massless light itself cannot escape once it crosses this boundary, the event horizon marks the edge of what is in any practical sense knowable. What lies inside is for now beyond the reach of observation. Scientists sometimes describe this as one of the most honest admissions in all of physics. Not that we haven't looked hard enough, or that our instruments aren't sensitive enough, but that the structure of the universe itself places a limit on what can be known from outside. The event horizon is not a failure of science. It is a feature of reality. There is something almost restful about that. About a universe that contains, built into its very architecture, a region of permanent privacy. The size of the event horizon, the radius of that boundary measured from the center outward, depends entirely on mass. Physicists use a calculation developed by the German astronomer Karl Schwarzschild, who worked out the mathematics while serving on the Eastern Front during the First World War in circumstances of extraordinary difficulty. His solution described the geometry of spacetime around a perfectly spherical, non-rotating mass. The resulting value, now called the Schwarzschild radius, tells you how small a given mass would need to be compressed to form a black hole, or equivalently, how large the event horizon of a black hole of that mass would be. For the Sun, the Schwarzschild radius is about 3 kilometers, meaning if the entire mass of the Sun were somehow compressed into a sphere 3 kilometers across, a black hole would form. The Sun, of course, is nowhere near dense enough for this to happen naturally. Its own thermal pressure, the energy released by nuclear fusion in its core, pushes back against gravitational collapse and keeps it stable. For the Earth, the Schwarzschild radius is even smaller, about 9 millimeters, roughly the size of a marble. And for Ton 618, with its mass of around 66 billion suns, the Schwarzschild radius stretches to approximately 1,970 astronomical units, an astronomical unit being the average distance between the Earth and the Sun, which means the event horizon of Ton 618 extends in every direction from its center for nearly 2,000 times the distance from here to the Sun. The entire orbit of Neptune, the outermost of our 8 planets, sitting about 30 astronomical units from the Sun, would fit inside that event horizon with room to spare. Many times over. Researchers have noted that when people first encounter this comparison, there is often a brief pause. Not alarm exactly, more like a quiet recalibration. The mind adjusts its sense of scale, and for a moment, everything familiar becomes very small. And yet the event horizon itself is invisible. This is worth sitting with. Something the size of 2,000 astronomical units, an object vastly larger than our entire solar system, and you cannot see it. Not because it is too far away, though it is. Not because our instruments are insufficient, though they are tested by it. But because the very nature of the boundary is defined by the absence of escaping light. The event horizon does not shine. It does not radiate. It is defined precisely by what does not come out of it. What we detect instead are the effects. The accretion disk, the swirling material falling inward from outside the event horizon, heated to extraordinary temperatures by compression and friction, glowing intensely across multiple wavelengths. The jets of material and energy that some black holes project outward along their rotational axes, streams of plasma moving at speeds approaching the speed of light. The subtle warping of light from background objects bent by gravity as it passes near the event horizon, a phenomenon called gravitational lensing, which can produce rings and arcs of distorted light around particularly massive objects. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, not the hole itself, but the dark region at its center, surrounded by the glowing ring of the accretion disk. It was a blurry orange-toned circle, unglamorous in a way, and yet scientists around the world, many of whom had spent years on the project, found themselves genuinely moved. Because that fuzzy circle was in a very real sense a portrait of absence, a photograph of a place from which no photograph could ever be taken. There is something in that paradox that the mind doesn't quite finish processing. It just holds it quietly and lets it stay unresolved. Perception, neuroscientists have observed, is not a passive reception of information. The brain is always actively constructing what it experiences. When you look at something, your visual cortex is not simply recording photons that arrived at your retina. It is interpreting, filling in, predicting, resolving ambiguity, drawing on memory and expectation to build a coherent picture from what is actually a surprisingly incomplete input signal. The sharp, detailed, colorful world you perceive is to a significant degree a model, an inference, a best guess made continuously and unconsciously about what is actually out there. This means that in some sense, you have never directly seen anything. You have seen the brain's interpretation of what was there. The gap between the two is usually small enough to ignore. But in certain conditions, in low light, in unfamiliar environments, in the borderland between waking and sleep, that gap can become more noticeable. The construction becomes visible as construction. The model shows its seams. Scientists suggest that this is one reason why the hours near sleep are so often accompanied by unusual imagery, by thoughts that feel slightly sideways, by a loosening of the ordinary confidence that what we perceive is simply what is there. The brain's predictive systems are winding down. The tight, efficient inferencing of waking life is softening into something more open-ended, more willing to simply not know. In that state, the idea of something defined entirely by its absence, the event horizon, the place the light does not return from, feels less like a physics concept and more like something recognized, something the mind already knows how to hold in its own quiet way. What remains at this hour is not a need to fully understand. The geometry of space-time near TON 618 will continue whether or not it is understood tonight. The event horizon will hold its boundary. The equations will stay true. And somewhere in the literature of theoretical physics, in papers dense with mathematics that most people will never read, the shape of that boundary is described with a precision that is in its own strange way beautiful, the way any honest description of a very large truth can be beautiful even when the truth itself remains in human experience just out of reach. Knowing the edges of things is its own kind of knowledge, knowing where understanding stops and what waits just beyond the stopping place. That is not ignorance, it is orientation. And from here, quietly oriented towards something vast and dark and perfectly still at its center, the mind can begin to let go of the effort of knowing, can begin to simply be in the presence of it, the way you might sit near the edge of a very deep, very still body of water at night and feel no need to cross it, just near it, just resting in the awareness that it is there. The distance from here to the next layer of understanding is not so different really from the distance light crosses on its long way home, and both in their own way are already underway. The human brain is extraordinarily good at numbers up to about 4. This is not a metaphor. Researchers who study numerical cognition have found that when a small number of objects, 3 dots, 4 birds, 2 stones, appears in front of a person, the mind registers the quantity almost instantaneously without counting. This ability is called subitizing, from a Latin root meaning sudden, and it appears to be something the brain does automatically without effort, the way it recognizes a familiar face or hears its own name in a crowded room. Up to 4, the mind simply knows. Beyond 4, something changes. The brain shifts into a different mode. It begins to count, or to estimate, or to rely on learned symbols. The word 7, the numeral 12, the abstract concept of 1,000, to stand in for quantities it cannot directly perceive. These symbols work. They are enormously useful, but they are not the same as knowing. They are representations of quantities the mind can manipulate without ever truly feeling. And this gap between the numbers we can hold in direct awareness and the numbers we can only handle symbolically grows wider the further out you go. A million is a symbol. A billion is a symbol. 66 billion is a symbol, carrying a weight that has no experiential equivalent anywhere in an ordinary human life, which is where TON 618 quietly resides, in the space beyond feeling, in the place where numbers go when they outgrow the mind's ability to receive them as anything other than marks on a page. 66 billion solar masses. That is the current best estimate for the mass of TON 618, derived from careful measurements of the gas moving at high velocity in the region surrounding it, gas whose speed tells astronomers, through well-understood physics, how much gravitational pull it is orbiting around. To try to approach this number from a human direction, our Sun contains within its volume roughly 1.3 million Earths. It holds more than 99% of all the mass in the solar system. The planets, the moons, the asteroids, the comets, everything else combined amounts to less than 1% of what the Sun holds. The Sun is by any ordinary measure an almost inconceivably large object, and TON 618 outweighs it 66 billion times over. Researchers have sometimes tried to communicate this through comparison. If you were to line up solar masses the way you might count coins, 1, 2, 3, and you counted one per second without stopping, without sleeping, it would take you more than 2,000 years to reach a billion. To reach 66 billion, you would need to count for roughly 2,100 years, longer than recorded history in many parts of the world, longer than the interval between now and the time of ancient Rome. And each one of those counted masses would be the Sun, would be this enormous ancient gravity-dominant star at the center of everything we have ever directly known. The mind attempts this and then gently stops, not in frustration, more like a traveler reaching the edge of a known map and simply standing there, looking into what the map does not show. There is a concept in psychology called number sense, the intuitive embodied feeling for quantity that develops early in childhood and remains with us throughout life. Number sense is what lets you estimate whether a jar holds 50 beans or 500 without counting. It is what makes a crowd of 20 feel different from a crowd of 200. It is rooted in experience in the body, in the accumulated weight of having lived in a world where quantities have physical presence. Neuroscientists have found that number sense operates through specific regions of the brain, particularly an area called the intraparietal sulcus, a fold in the parietal lobe that appears to be involved in spatial reasoning, magnitude comparison, and the general sense of more and less. This region is active when you judge whether something is bigger or smaller, heavier or lighter, nearer or farther. It is, in a sense, the brain's built-in measurement system. But this system was built for the world at human scale. For distances you can walk, quantities you can carry, times you can survive to see. When numbers approach the scale of galaxies and geological eons and masses measured in multiples of stellar objects, the intraparietal sulcus has nothing to calibrate against. The measurement system reaches for a reference point and finds none. And in that absence, something interesting happens. The brain does not panic. It does not error. It simply generates a kind of quiet awe, a response that researchers have begun to study more carefully in recent years, finding that it is associated with a distinctive physiological signature: slowed breathing, reduced heart rate, a slight expansion of peripheral awareness. The body, when confronted with something genuinely beyond its scale, tends to settle rather than accelerate, to open rather than tighten. Scientists suggest this response may have very old roots. The experience of standing under a vast open sky, or at the edge of an ocean, or inside a large and ancient forest, these encounters with scale have been part of human life for as long as there have been humans. And the body seems to have learned over that long time that enormity is not a threat, that something being incomprehensibly large does not mean it wishes you harm, that the correct response to vastness is not alarm, but a kind of reverent stillness. You may be feeling something like that right now. The category of objects to which TON 618 belongs, ultramassive black holes, with masses exceeding roughly 10 billion solar masses, represents a kind of upper limit that astronomers are still trying to understand. Most black holes, even the supermassive ones at the centers of galaxies, fall well below this threshold. The supermassive black hole at the center of our own Milky Way, called Sagittarius A, has a mass of around 4 million solar masses, which is itself an extraordinary number, but one that seems almost modest next to what sits at the heart of TON 618. The question of how black holes grow to ultramassive scales is one that researchers are still working through. The leading understanding involves a combination of processes, the merger of galaxies, each bringing its own central black hole, which then combine. The rapid accretion of material during early periods of the universe, when gas was more abundant and less dispersed, and possibly some conditions in the early cosmos that allowed black holes to form with higher initial masses than the ones being created today. What seems clear is that objects like TON 618 required particular conditions, a particular convergence of environment and time and available material that may not easily repeat. They are, in a sense, relics, artifacts of a younger, denser, more turbulent universe. The ultramassive black holes we can detect today are most of them not actively growing in the way they once did. They have entered a quieter phase, settled into the centers of their galaxies, become still. There is something worth sitting with in that image, something that was once consuming material at extraordinary rates, pouring out energy visible across billions of light years, now quiet, now simply massive, now defined not by activity, but by presence, by the patient, unchanging fact of its own weight. Weight in the physics of very large objects becomes a fundamentally different thing from weight as we experience it daily. When you feel weight, the heaviness of your body against a mattress, the pull of gravity that keeps you grounded, you are experiencing the curvature of space-time created by the Earth's mass. The Earth is pulling you not through a mysterious force reaching across space, but by the shape it imposes on the space around you. You follow that shape the way a marble follows the curve of a bowl, naturally, without effort, without resistance. Near TON 618, that curvature would be extreme beyond any direct comparison. The region of space-time around its event horizon is so deeply curved that the mathematics describing it requires careful handling even for physicists. The paths available to matter and light near that boundary are dramatically narrowed. Options close. Trajectories converge. Everything that enters a certain zone finds itself guided unavoidably toward the center. And yet, at a safe distance, at the scale of the galaxy surrounding it, which is itself enormous, the effects of that gravity are simply part of the structure. The stars in that galaxy orbit at distances where the pull, while strong, is navigable. They move in their long ellipses around the central mass, the way Earth moves around the Sun, steadily, continuously, following the shape of a space that has been the same for them for millions of years. Researchers have noted something philosophically interesting here. An object of enormous gravitational influence at the right distance does not pull everything into itself. It organizes. It creates stable patterns. The same force that up close permits nothing to escape at a greater distance becomes the quiet, consistent architecture around which systems persist. Mass at sufficient scale becomes structure, becomes the thing that holds other things in their paths. The mind cognitive scientists have observed has a somewhat similar relationship with large, stable structures. When we exist within systems that are much larger than ourselves, families, communities, institutions, the long, unbroken continuity of the natural world, there is a particular kind of ease that becomes available. Not the ease of having nothing to worry about, but the ease of knowing that something vast and stable underlies the immediate moment, that the ground, in some essential sense, continues beyond whatever is happening on its surface. This is different from certainty. It is closer to what psychologists call secure attachment, the felt sense that there is something reliable in the background, not demanding attention, simply present. Research suggests that this background sense of stability actively supports the nervous system's ability to rest. When the mind perceives itself within a larger, steady context, the vigilance systems that evolved to scan for threat find less to do. They quiet. They allow the rest of the brain to soften into whatever comes next. TON 618 has been at the center of its galaxy for a very long time. Its presence there is not new. The structures that formed around it, the stars, the dust clouds, the slow orbital dances of many billions of years have been finding their balance around that central mass for longer than the Earth has existed. There is a stillness to that, a deep, impersonal, entirely unhurried continuity. And if the mind at this hour needs something stable, to rest against something enormous and quiet and entirely indifferent to the small turbulences of any single night, there is at least that. Somewhere very far from here, at the center of something very large, something very heavy, is simply sitting still, and has been for longer than we have words to describe. The numbers that describe it, the billions of solar masses, the thousands of astronomical units, the millions of years of quiet gravity, these are not the point really. They are doorways, ways of approaching something that cannot be approached directly, ways of letting the mind expand past its usual boundaries, not all at once, not with effort, but gently. The way a room seems larger in the dark than it does in the light. There is more to come in understanding what an object this massive does to the space around it, what it means for time to slow near a gravity well of that depth, what it means for light and for matter and for the strange boundary where the known gives way to something the equations describe but experience cannot follow. These ideas are quiet and patient. They are not going anywhere, and neither at this hour are you. Friction is one of the oldest forces in human experience. The warmth of two hands rubbed together, the spark from stone against stone, the slow heat that builds in any system where things are moving in contact with each other, where edges meet and pressure builds and energy has nowhere to go but out. Friction is so ordinary, so constantly present in daily life that it barely registers as a phenomenon. It is simply the texture of a physical world where things touch and push and slow each other down. And yet, in certain contexts at certain scales, friction becomes something else entirely. Something that generates not just warmth, but light. Not just light, but radiation across the entire electromagnetic spectrum. Not just radiation, but outpourings of energy so vast that they can be detected across distances measured in billions of light years. This is what happens in the accretion disk surrounding a black hole like TON 618. An accretion disk forms when material gas, dust, the remnants of disrupted stars, the diffuse matter drifting through galactic space, falls toward a black hole but does not fall in directly. Because that material almost always carries some rotation, some angular momentum, it cannot simply drop straight down the gravitational well. Instead, it begins to orbit. It settles into a disk shape, the way water spiraling toward a drain flattens into a rotating sheet before it descends. But unlike water in a drain, this material is not moving in a single orderly current. Different parts of the disk orbit at different speeds. Inner regions move faster, outer regions slower, just as the inner planets of our solar system orbit the Sun more quickly than the outer ones. And because adjacent layers of the disk are moving at different velocities, there is constant friction between them, constant collision, constant transfer of energy. That friction heats the disk to extraordinary temperatures. Researchers have found that in the innermost regions of an active accretion disk around a supermassive black hole, temperatures can reach into the tens of millions of degrees. At those temperatures, matter does not simply glow with visible light. It radiates across a much wider range in ultraviolet, in X-rays, in forms of energy far more penetrating than anything produced by ordinary stellar processes. A quasar, which is what TON 618 was at its peak of activity, is essentially a black hole whose accretion disk is operating at extraordinary intensity, feeding, consuming, generating luminosity that can at its brightest outshine every star in its host galaxy combined. Not slightly, not modestly, by factors that are themselves difficult to hold in ordinary imagination. The luminosity of the most powerful quasars, the most actively feeding supermassive black holes, has been measured at something in the range of 1 trillion times the output of the Sun. 1 trillion individual stars, each burning with the full energy of our solar system's center, all compressed into a region not much larger than our solar system itself. That is the energy density of a quasar at full activity. TON 618, when it was actively feeding billions of years ago, would have been among the brightest objects in the observable universe. The galaxy surrounding it, its stars, its gas clouds, its own ancient light, would have been almost invisible in comparison, drowned out by the blazing output of the central engine. And now from here, from this quiet room on a small planet orbiting an unremarkable star on the outer edge of a spiral galaxy, we receive the faintest echo of that output, stretched by redshift, dimmed by distance, arriving as a signal so faint it requires instruments of considerable sensitivity to detect at all. The trillion sun blaze reduced across the enormity of space and time to a whisper. There is something in that transformation from unimaginable brightness to barely detectable signal that the mind receives not as loss, but as a kind of peace. As if extreme things given enough distance and enough time eventually become quiet. The process of accretion of material spiraling inward and releasing energy as it goes is one of the most efficient energy-generating processes in the known universe. More efficient by a significant margin than nuclear fusion, which is the process that powers stars. In nuclear fusion, matter is converted to energy at an efficiency of roughly a fraction of a percent less than 1 part in 100 of the mass involved becomes energy. The rest remains as matter in a different form. In accretion onto a black hole, depending on the spin of the black hole and the geometry of the disk, the efficiency can reach several percent, and in some theoretical configurations, up to around 40%. 40% of the mass of the infalling material converted directly into energy. This is the physics reason why quasars can be so extraordinarily bright while consuming what is relative to their output a modest amount of material. A black hole, accreting even a few solar masses of material per year, can outshine an entire galaxy. Scientists describe accretion disks as some of the most energetically extreme environments in the universe, and yet the physics governing them is at its core the same physics as water circling a drain, the same physics as the warmth in your hands after rubbing them together. Scale changes everything about the experience, but the underlying principle, friction, angular momentum, conservation of energy, remains the same. There is something unexpectedly grounding about that. The idea that the most violent energy-releasing processes in the universe operate on the same basic rules as the most ordinary ones. That the cosmos, for all its scale, is using a consistent vocabulary, a shared grammar of physical law that runs from the smallest to the largest without interruption. The human body has its own version of this, its own accretion in a loose sense, not of matter falling toward a gravitational center, but of attention moving toward what draws it. Psychologists have observed that the mind naturally organizes itself around whatever it finds most compelling in a given moment. Thoughts gather, associations accumulate. The mental equivalent of a disk begins to form with the point of focus at its center and related ideas orbiting at varying distances. This is part of what makes the hours near sleep so distinctive. As the day's accumulated focus begins to release, as the tasks and conversations and unresolved thoughts stop demanding attention, the mind's accretion disk, in a sense, begins to thin. The orbiting material slows. The inner heat dissipates. What was a tight, organized system of focused attention gradually loosens into something more diffuse, more spacious. Researchers who study the transition between waking and sleep have found that this loosening is associated with a shift in the brain's electrical activity from the faster, higher frequency waves associated with active thinking towards slower rhythms that characterize relaxation and early sleep. This shift is not a loss of the mind. It is a different mode of the mind, one in which the tight, sequential logic of daytime thinking gives way to something more associative, more drifting, more willing to make unexpected connections between things that seem on the surface unrelated. Scientists sometimes call this the hypnagogic state, the threshold between waking and sleep, where the mind is still generating experience, but no longer firmly anchored to the external world. It is in this state that people often report unusual imagery fragments of thought that feel almost like dreams, a loosening of the ordinary sense of where the self ends and everything else begins. The slow drift of ideas about distant black holes, about friction and luminosity, and the long journey of light. These are perhaps exactly the kind of material that moves gently through that threshold, not demanding to be solved, not requiring a response. Simply present the way the accretion disk of a distant quasar is present somewhere out there, generating its quiet light, not needing to be witnessed to continue. There is a particular quality of light that accretion disks produce called synchrotron radiation. It arises when charged particles, electrons moving at speeds approaching the speed of light, spiral through magnetic fields. As they curve through those fields, they emit radiation, and the spectrum of that radiation carries a distinctive signature that astronomers have learned to recognize. Synchrotron radiation was first observed in particle accelerators on Earth before it was understood to be a major source of light in astrophysical settings. It is now known to be responsible for much of the radio emission from active galactic nuclei, from jets from the regions surrounding powerful black holes. The word synchrotron comes from the name of the type of particle accelerator in which it was first observed, a machine that uses magnetic fields to guide particles in circular paths, accelerating them to high energies. The connection between laboratory physics and cosmic physics here is not metaphorical. The same phenomenon operating under the same physical laws produces the same kind of light, whether it occurs in a machine the size of a building or in a region of space larger than our solar system. Researchers have noted that this kind of physical consistency, the same laws producing the same effects at vastly different scales, is one of the deep, quiet reassurances of science. The universe does not have separate rules for small things and large things, for near things and far things. The rules are the same everywhere they have been tested, which means that what we learn here in laboratories and in the careful study of the natural world at human scale genuinely applies to places we will never visit and scales we will never directly experience. The laws of friction that warmed the accretion disk of TON 618 into trillion sun luminosity are the same laws that warm your hands on a cold night. There is a connection there, small perhaps, easily overlooked, but real. The jets that some black holes produce narrow streams of plasma and energy launched outward along the rotational axis, sometimes extending for thousands of light years, are among the most dramatic expressions of the accretion process. They arise from complex interactions between the infalling material, the magnetic fields threading through the disk, and the rotation of the black hole itself. The physics of jet formation is still an area of active research. Scientists are still working to understand exactly how so much energy gets focused into such a narrow stream, how these jets maintain their coherence across such enormous distances, what ultimately determines their direction and duration. What is understood is that these jets can carry enough energy to affect the galaxies they pass through. They can heat surrounding gas clouds, suppress the formation of new stars, reshape the structure of the host galaxy over millions of years. A black hole's influence, it turns out, does not end at the event horizon. It extends through gravity, through radiation, through jets, far into the space around it. The mind neuroscientists have observed works in something like this way too. The most significant things that happen in a person's inner life do not stay contained at the point where they occurred. They radiate outward. They reshape the landscape of memory and attention and emotional tone in ways that continue long after the original event has passed. A single thought, arriving at the right moment, can redirect the current of a whole night's experience. But that is perhaps a thread for another part of the journey. For now, what remains is the image, the great disk of heated, spiraling material, the outflow of light in all directions, the long, slow dimming of something that was once extraordinarily bright, across a distance so great that by the time its light reaches here, it has become the quietest possible signal. Still arriving, still in its own way, warm. And beyond the disk, beyond the jets, beyond the observable edge of the galaxy that holds all of this, there is the question of what the universe itself was doing in that early active time. What surrounded TON 618 as it fed? What the cosmos looked like when it was young and dense and lit from within by 1,000 brilliant engines like this one? That universe is still out there in a sense, still visible in the stretched and shifted light of the most distant objects. A record of a time the universe has moved through, but not forgotten. Every photograph is a record of light that no longer exists in quite the same form. The moment the shutter closes, the light that made the image has already moved on. The scene that was captured is already slightly different. A shadow has shifted, a person has turned, the quality of afternoon has leaned a degree closer to evening. The photograph holds a version of that moment fixed, while the moment itself continued forward without stopping. This is true of every image ever made, and in a quieter way, it is true of every act of perception. By the time light has traveled from a surface to your eye, been converted to a neural signal, and been processed into something you recognize as seeing the original event, has already passed. Most of the time, this delay is so small it makes no practical difference. The gap between event and perception is measured in fractions of a second. But at cosmological distances, that gap becomes something far more significant. Something that changes in a fundamental way what it means to look at something at all. The light currently arriving from TON 618 left its source when the universe was roughly 1.5 billion years old. The universe is now around 13.8 billion years old, which means that what we observe when we study TON 618 is a window into a time when the cosmos was approximately 10 to 11% of its current age. A young universe, a very different universe, one that operated in some ways by the same physical laws as now, but looked and behaved almost nothing like what we see around us today. In its earliest phases, the universe was extraordinarily hot and extraordinarily dense. The Big Bang, the rapid expansion from an initial state of enormous energy density, had left behind a cosmos filled with a plasma of fundamental particles so energetic and so compressed that light could not travel freely through it. Photons were constantly absorbed and re-emitted, trapped in a fog of charged particles, unable to move more than a short distance before being intercepted again. This period lasted for roughly 380,000 years. Then, as the universe expanded and cooled to a temperature where electrons could combine with protons to form neutral hydrogen atoms, the plasma cleared. The fog lifted. Light was suddenly free to travel. And the first photons to cross the now transparent universe have been traveling ever since, stretched by the expansion of space into the microwave range detectable today as a faint background radiation that fills the sky in every direction. Cosmologists call this the cosmic microwave background, and it represents the oldest light we can directly observe. A photograph taken when the universe was less than 400,000 years old. The time between that clearing fog and the era when TON 618 was active, roughly 1 billion years, was a period that researchers sometimes call cosmic dawn. It was during this interval that the first stars ignited, the first galaxies began to assemble, and the universe transitioned from a relatively uniform sea of hydrogen and helium into the structured, textured cosmos of stars and galaxies and great cosmic filaments that we inhabit today. Scientists are still working to understand cosmic dawn in detail. It sits near the edge of what current instruments can observe in a regime where the signals are faint and the interpretation is challenging. But what is understood suggests that this was a period of rapid dramatic change. The first stars were likely very different from the stars we see now, larger, hotter, shorter-lived, burning through their fuel in millions rather than billions of years. The first galaxies were smaller, more irregular, colliding and merging more frequently in a universe that was denser and more chaotic than today's. It was into this early turbulent cosmos that TON 618 was born. How a black hole as massive as TON 618 could have formed in the first billion years of the universe is a question that genuinely puzzles researchers. The standard pathways for black hole formation, the collapse of massive stars at the end of their lives, the gradual accretion of material over long periods, seem too slow, too modest, to account for something with 66 billion solar masses existing so early in cosmic history. The universe simply had not had enough time, by conventional reasoning, to build something that large through ordinary processes. Several ideas are being explored. One possibility is that the very first black holes were not formed from stellar collapse at all, but from the direct collapse of enormous clouds of primordial gas clouds so massive and so lacking in the metals that normally fragment gas into smaller star-forming clumps that they could collapse wholesale into black holes of intermediate or even large initial mass. These hypothetical objects are sometimes called direct collapse black holes, and if they existed, they would have given the early universe a head start seed. Black holes already much larger than stellar remnants, ready to begin accreting material from the surrounding environment. Another possibility involves the mergers of smaller black holes in the dense collision-prone environment of the early universe, a kind of hierarchical assembly building up mass through a series of coalescences, each one adding to the total. The early universe's higher density would have made such mergers more frequent than they are today, potentially allowing rapid growth that slowed as the cosmos expanded and the galactic environment became less crowded. Researchers have found that neither explanation alone fully accounts for what they observe. The puzzle of how the most massive black holes grew so large so quickly in the early universe is one of the genuinely open questions in modern cosmology. One of those places where the known and the unknown meet, and where the meeting is honest enough that scientists will tell you directly, "We are still working this out." There is something almost companionable about that admission, about knowing that the universe contains puzzles that the most careful and rigorous minds are still sitting with, still turning over, quietly, still approaching from different angles in search of the right question. The era of cosmic dawn was also, researchers believe, the period of reionization, a phase transition in the state of the universe's hydrogen that has left its signature in the light from distant quasars like TON 618. After the cosmic microwave background was released, the hydrogen filling the universe settled into a neutral state, atoms with their electrons paired and bound. But as the first stars and galaxies lit up, their ultraviolet radiation began stripping those electrons free, again ionizing the surrounding hydrogen. This process spread outward from early galaxies like light spreading through mist, slowly clearing the neutral hydrogen from the intergalactic medium over the course of several 100 million years. By the time TON 618 was actively feeding, by the time the light now arriving on Earth had already begun its journey, reionization was largely complete. The universe had cleared again in a different way than before, not from recombination, but from being flooded with enough energetic radiation to keep the intergalactic gas ionized and transparent. The quasars themselves, TON 618, among them, likely contributed to this process. Pouring out ultraviolet and X-ray radiation in enormous quantities, they would have ionized vast regions of surrounding space, pushing back the neutral hydrogen and contributing to the clearing of the cosmic fog. In a very real sense, the early universe's most powerful energy sources helped make the universe transparent, helped create the conditions under which light could travel freely across cosmological distances. And then their work in some sense done, they quieted. The feeding slowed. The accretion disks thinned. The great engines that had blazed through the early cosmos gradually wound down as the available fuel. The dense clouds of gas that had surrounded them was consumed or dispersed. Quasars became less common as the universe aged. The ones that remain active today are fewer, and the ones that have gone quiet, like most likely TON 618, sit at the centers of their galaxies in a kind of permanent retirement. This arc from blazing intensity to deep quiet is one that the universe seems to follow at many scales in many contexts. Stars burn and cool. Galaxies evolve from active star-forming regions into older, quieter collections of aging stars. Even the universe itself, in the very long run, is expected to gradually wind down from its current level of activity into something cooler, dimmer, more still. Scientists suggest this is not a tragedy. It is simply the direction that entropy moves from concentrated structured energy toward more distributed, more diffuse forms, from bright to quiet, from active to resting. There is a kind of rhythm to it if you hold it lightly enough to feel. Memory, psychologists have found, is not a recording. It is a reconstruction. Each time a memory is recalled, the brain does not simply retrieve a stored file and play it back. It rebuilds the memory from its component parts, the sensory details, the emotional context, the surrounding associations, assembling them in the moment of recall, influenced by everything that has happened since the original event. This means that memories change slightly each time they are accessed. They are colored by the present. They carry traces of every retrieval they have been through. An old memory recalled many times is in some sense as much a record of all those recollections as it is of the original experience. Researchers have found that this reconstructive quality of memory is not a flaw. It is, in fact, what allows memory to be useful. A memory that could not be updated would not serve a changing organism in a changing world. The ability to integrate new information into old records to allow the past to be gently reshaped by the present is part of what keeps the mind flexible, part of what allows learning and adaptation to continue throughout a life. The light from TON 618, in its own way, is a record that has been shaped by everything it crossed. It left its source as one thing and arrived here as something slightly different, stretched, filtered, bent by the geometry of the space it traversed. It carries the original signal, but also carries the journey, both at once, inseparable. Perhaps this is true of most things that travel far enough. They arrive changed, and the change is part of what they bring. The universe that existed when that light departed, young, dense, actively constructing itself, brilliant with the fires of early galaxies, is not gone. It is recorded in the light, still arriving from those distances, in the microwave background, still filling the sky, in the ratios of elements, in the oldest stars, still burning in the halos of galaxies, in the large-scale structure of the cosmic web, the filaments and voids and clusters of galaxies that formed in the early universe and still carry in their arrangement the imprint of conditions that existed billions of years ago. The early universe is still here in its way, encoded in the present, carried forward in the light, and the question of what any of it means, what it means for something to be this old, this large, this patient, is not one that needs to be answered tonight. It is one that the mind can simply hold, the way it holds a piece of music it doesn't fully understand, but finds, for reasons it cannot articulate, beautiful. Some things are better received than analyzed, better felt than explained. And at this hour, with the room quiet and the mind beginning its own slow drift towards something older and quieter than waking thought, that distinction matters less and less. What remains is simply the sense of it, the long, uninterrupted arc of time, the light still coming, the universe in its patient way still telling its own story, and somewhere in that story, written in physics, and in the stretched wavelengths of ancient radiation, there is something that science can measure, but perhaps only night can fully convey. The way that what is very far away can, in the right conditions, feel surprisingly close. There is a particular kind of listening that happens not with the ears, but with everything else. You have probably done it without naming it. Standing very still in a place you don't quite recognize, reading the space through some combination of air pressure and sound, and the subtle way that silence has a different texture depending on what surrounds it. Or lying in the dark and knowing before any sound confirms it that rain is coming. Something in the atmosphere, the particular quality of the quiet, a drop in pressure that the body registers before the mind catches up. The senses, when vision is removed or reduced, redistribute themselves. They find other ways in. They learn to read what is present through what cannot be directly seen. This is in essence what scientists have done with black holes. Not with any single instrument, not through any single method, but through a long and patient accumulation of indirect readings of what the surrounding material is doing, of how the light behind bends, of how the gas moves, of what frequencies arrive, and in what proportions assembled into something that approaches, if not a direct portrait, then at least a reliable map of something that has never been and cannot be directly observed. The technique called reverberation mapping is one of the most elegant examples of this indirect listening. It works on the principle of echo. When the central engine of a quasar, the region very close to the black hole, where the most energetic radiation is produced, fluctuates in brightness, that fluctuation sends a signal outward in all directions. Some of that signal travels directly toward the observer. Some travels outward and strikes the broader region of gas surrounding the black hole, a region called the broad line region, where clouds of gas orbit at high velocities and respond to incoming radiation by emitting light of their own at specific characteristic wavelengths. Because the broadline region is physically larger than the central engine, the signal takes longer to reach it than it takes to reach the observer directly. The gas responds to the fluctuation, but with a delay, and that delay measured in days or weeks or months, depending on the size of the system, tells astronomers the physical scale of the broadline region. The larger the delay, the larger the region, and from the size of the region, combined with measurements of how fast the gas in that region is moving, information carried in the width of the spectral lines, it emits lines that broaden when the gas is moving rapidly toward and away from the observer. Astronomers can calculate the mass of whatever is holding that gas in orbit, the gravitational influence that determines the orbital speed, the mass at the center. Photon 618. This method has yielded the estimate of approximately 66 billion solar masses, not measured directly, not weighed on any scale, but derived from the careful reading of a delay from the patient comparison of a signal and its echo from the understanding that time measured with precision carries information about space. Scientists who use this technique sometimes describe it as listening to a room by its reverb. The size and shape of a space can be inferred from the way sound bounces through it, the way an echo returns. A small room echoes quickly, a large hall takes longer, and the difference measured carefully tells you something true about the geometry of what you cannot see. The history of astronomy is in large part a history of learning to read indirect signals. For most of human history, the only tool available was the unaided eye. And even then, what the eye received was not direct contact with the objects being observed, but light that had traveled from them, carrying information about their surfaces and temperatures and motions encoded in its spectrum. The invention of the telescope in the early 17th century extended this reach, gathering more light-resolving finer details, but still working entirely through the medium of visible light. Then, in the middle of the 20th century, radio astronomy opened an entirely new window. Carl Jansky, an American physicist working for a telecommunications company in the 1930s, was investigating sources of static that were interfering with transatlantic radio communications. He systematically tracked down various sources of interference thunderstorms nearby electrical equipment and found to his considerable surprise that one source rotated with the sky. It was not terrestrial in origin. It was coming from space. Specifically, he determined from the direction of the center of the Milky Way. Jansky had discovered that the universe was emitting radio waves, that there were processes out there, some of them, it would later be understood, associated with the most extreme objects in the cosmos generating radiation at wavelengths far below what the eye could detect. A new kind of listening had become possible, and with it, an entirely new universe began to come into focus. TON 618 itself was first identified as a radio source, catalogued not for its visible light, but for the radio waves it was emitting. It was given a designation from the catalogue of radio sources compiled by astronomers working to map these new signals, TON 618, from the 3rd Ohio Survey of Radio Sources. For some years after its initial detection, its nature was not fully understood. It appeared as a faint optical object at the position of the radio source, not obviously different from many other faint objects in the same region of sky. It was only through careful spectroscopic analysis, the measurement of its redshift from the characteristic wavelengths of its light, that its true distance, and therefore its extraordinary luminosity, was revealed. A catalogued noise patiently followed led to one of the most massive objects ever measured. Spectroscopy is the science of decomposing light into its component wavelengths and reading what those wavelengths reveal. Every element, when energized, emits light at specific characteristic wavelengths, a kind of fingerprint, unique and consistent, that allows the composition of a distant object to be determined from the light it sends. Hydrogen emits at certain wavelengths, helium at others. Calcium, iron, magnesium each leaves its own signature in the spectrum of a star or a gas cloud or an accretion disk. When that spectrum is shifted, when all the characteristic lines are moved together toward longer wavelengths, the shift tells you the velocity of the source relative to the observer. And when the shift is toward longer wavelengths, the source is moving away. The universe's expansion means that distant objects are moving away from us, and the further they are, the faster they recede, and the greater the shift in their spectral lines. From these shifts measured with care, cosmologists can determine distances that no instrument could directly span. The spectrum of a distant quasar, analyzed in a laboratory, yields the redshift, which yields the recession velocity which through the well-understood relationship between velocity and distance in an expanding universe yields the distance. Billions of light-years derived from the careful reading of where a spectral line falls relative to where it should. Researchers have noted that this chain of inference from wavelength to velocity to distance to cosmic history is one of the most impressive feats of applied reasoning in all of science. It is indirect at every step, and at every step it has been tested, checked, cross-referenced with independent methods, and found to be reliable. The universe, when you learn its language, turns out to be surprisingly willing to answer questions about itself. The language it happens is light, and the grammar is physics. There is a form of human listening that works in a similar way, building a picture of something not directly accessible from the signals it sends through what surrounds it. Psychologists who study emotional intelligence have observed that much of what we understand about other people's inner states does not come from what they say directly. It comes from the secondary signals, the small hesitations, the particular quality of a silence, the way energy shifts in a room when someone enters or leaves. We read these signals automatically below the level of conscious analysis, assembling from fragments of indirect information a sense of what is present that often turns out to be remarkably accurate. This form of perception, indirect assembled patient, is, researchers suggest, one of the brain's older and more reliable capacities. It predates language. It predates the kind of linear verbal reasoning that occupies most of waking thought. It operates through different neural pathways, processes information differently, arrives at conclusions through means that are not fully transparent even to the person doing the perceiving. At night, when the more recent and more effortful forms of cognition begin to quiet, this older form of perception tends to become more prominent. The mind, no longer occupied with the explicit processing of language and logic, becomes more sensitive to pattern, to rhythm, to the subtle signals that move through a space without announcing themselves. Scientists sometimes describe this as a shift from top-down to bottom-up processing, from cognition driven by expectations and frameworks to cognition driven more directly by incoming signal. It is a more open, more receptive mode, less efficient in some ways, more sensitive in others. And in that sensitivity, in that particular quality of nighttime awareness, certain things become perceptible that the busy daytime mind tends to filter out. The temperature of the air, the weight of the quiet, the faint background of sound that is always present but rarely attended to. The body doing what it does, breathing, circulating, slowly releasing the tensions of the day. The universe doing what it does, expanding, cooling, sending its ancient light across distances that have no name in ordinary language, both in their way simply continuing. The Event Horizon Telescope. The collaboration that produced the first image of a black hole's shadow works on a principle called very long baseline interferometry. Radio telescopes positioned at different locations around the Earth, in Hawaii, in Chile, in the American Southwest, in Europe, in Antarctica, observe the same source simultaneously. The signals they collect, recorded with atomic precision, are then combined and compared. Because the telescopes are separated by distances as large as the diameter of the Earth, the combined instrument has an effective resolution equivalent to a telescope that size. The technique requires extraordinary coordination. The clocks at each telescope must be synchronized to within a fraction of a nanosecond, a billionth of a second, using atomic clock technology. The data volumes are so large that the recordings must be physically transported to a central location for processing. The final image emerges not from any single observation, but from the careful combination of signals from multiple instruments across multiple continents, aligned with a precision that researchers describe as genuinely difficult to overstate. And the result? That first orange glowing ring around a dark central shadow was not just a scientific achievement, it was a demonstration of something quieter. That patient coordination pursued over many years by many people using the most sensitive listening instruments ever built can reveal the outline of something defined entirely by what it does not emit. An image of absence made from presence. A portrait of silence drawn in light. There is something in all of this that the analytical mind can follow only so far before it reaches the edge of what analysis can hold. The rest, the feel of it, the quality of it, the way it settles in the chest at a particular hour of the night, that belongs to something else. Something that doesn't require understanding to receive. The body knows how to listen in the dark, has always known, has been doing it in one form or another for longer than there have been words to describe the experience. And at this hour, with the room quiet and the mind beginning to soften around its edges, that older form of listening is already active, already receiving, not needing to name what it hears, just open to it. And the next layer of this, the question of what it means for something to be as physically large as the event horizon of TON 618. What the actual dimensions of that space imply about everything that fits inside it that is already settling into place, gently, without effort. The way understanding always arrives at this hour when you stop reaching for it. Scale is something the body understands before the mind does. You feel it when you stand at the base of a very tall building and tilt your head back. When you look out from a high place over a wide valley. When you wade into the ocean and feel the floor drop away beneath your feet. The water deepening around you into something that no longer has a visible bottom. Before any number is processed, before any comparison is made, the body responds. The chest opens slightly. The breath shifts. Something in the nervous system recognizes that it is in the presence of something significantly larger than itself and adjusts accordingly. Researchers who study the psychology of awe have found that this physical response, the slight expansion of the chest, the slowing of breath, the momentary suspension of self-focused thought, is remarkably consistent across cultures and contexts. Whether the scale being encountered is geographical, architectural, or conceptual, the body's response shares the same signature. Something loosens. The boundaries of the self become very briefly less insistent. And in that loosening, there is often a quality that people describe not as fear, but as something closer to relief. As if the self had been holding itself very carefully, and the presence of something vastly larger gave it permission to set that effort down. This is the territory we are moving into now. Not fear, not alarm, just the quiet, gradual expansion that comes from approaching something whose dimensions require the mind to stretch in ways it does not usually stretch. The solar system, as a concept, has a way of feeling familiar without ever being truly felt. We grow up with images of it: the sun at the center, the planets arranged in their orbits, the whole thing presented as a neat diagram on a classroom wall or the screen of a phone. And in that diagrammatic form, it seems manageable, containable, something the eye can take in all at once. But the diagram is of necessity wildly distorted. If the sun were drawn at an accurate scale relative to the orbits of the planets, the paper required to show Neptune's orbit would need to be about 300 meters wide, while the sun itself would be a dot less than a millimeter across. The actual distances involved are so large and the objects so small relative to those distances that any true scale representation becomes essentially empty space with occasional tiny specks. The average distance from Earth to the Sun, called 1 astronomical unit, is roughly 150 million kilometers. Light covers that distance in about 8 minutes and 20 seconds. Neptune, the outermost planet, orbits at about 30 astronomical units from the Sun. The entire span of the solar system's planetary orbits from one side to the other is roughly 60 astronomical units across, and the Schwarzschild radius of ton 618. The radius of its event horizon is approximately 1,970 astronomical units. So the distance across the event horizon of ton 618 from one side to the other is something in the range of 3,900 astronomical units, more than 65 times the diameter of our entire planetary system. The orbit of Neptune, that distant cold world at the edge of what we think of as our cosmic neighborhood, would fit inside the event horizon of ton 618 more than 65 times over. The whole sweep of planetary space that humans have been dreaming about and slowly reaching toward since the first person looked up and wondered, all of it would be swallowed without remainder into a fraction of what ton 618 holds within its gravitational boundary. The mind receives this, pauses, and then does something interesting. It doesn't quite panic. It doesn't reject the information. It just sits with it for a moment, the way you might sit with a piece of music that contains more notes than you expected, waiting for the ear to find its footing. The concept of the Schwarzschild radius applies to any mass in principle. Every object has one, the theoretical radius to which it would need to be compressed for its escape velocity to reach the speed of light. For ordinary objects at ordinary densities, this compression is so extreme as to be essentially impossible under natural conditions. The Schwarzschild radius of a person, for instance, is smaller than an atomic nucleus. The Schwarzschild radius of the Earth, as noted earlier, is about 9 millimeters. What makes black holes unusual is not that they have a Schwarzschild radius, but that they have actually reached it. That the matter which once occupied a larger volume has been compressed through the force of its own gravity in the collapse of a massive star or through other pathways into a region smaller than this critical boundary. Once that threshold is crossed, there is no mechanism in known physics capable of reversing the process. The collapse continues. The matter falls inward. The event horizon forms and holds, maintained simply by the continued presence of mass within it. For ton 618, the event horizon is not the remnant of a single stellar collapse. The mass it contains represents the accumulated history of billions of years of feeding, merging growing a process of aggregation so slow and so vast that it almost defies the ordinary meaning of the word growth. It did not happen quickly. It happened the way geological formations happen, the way mountain ranges rise, the way ocean floors spread at a pace that the human experience of time cannot easily hold, but that leaves in the end something undeniably present, something with an event horizon 3,900 astronomical units across, something that from the outside is simply dark. Darkness, it turns out, is something the brain actively constructs rather than passively receives. In complete darkness, true darkness, without even the faint ambient light that usually finds its way into rooms at night, the visual system does not simply go quiet. It generates its own activity. Researchers have found that in the absence of external visual input, the brain continues to produce spontaneous neural firing in the visual cortex, and this activity can be perceived as faint shapes, movements, and patterns that seem to exist in the visual field even though nothing is actually there. This phenomenon, sometimes called visual noise or phosphenese, is the eye and brain producing experience from internal signal rather than external input. In other words, the mind, when deprived of the world to look at, begins to generate its own imagery, begins to see from the inside out. This is related to the dreaming process, the brain's capacity to construct full sensory experience from nothing but its own activity, and it becomes more pronounced as sleep approaches, as the filtering of external input relaxes and the internally generated signal grows relatively stronger. What the visual system does in darkness, other systems do in quiet. The auditory cortex without sound to process generates its own background. The body sense system without movement to track attends to subtler signals, the slow rise and fall of the chest, the rhythm of the pulse, the faint proprioceptive information of limbs resting against a surface. In the absence of the external world, the internal world becomes more present, more detailed, more available to awareness. Scientists suggest this inward turn is not random. It may serve a consolidating function, a period of internal review and integration that happens most easily when external demands are removed. The brain, no longer occupied with navigating the outer world, attends to its own maintenance, to the processing of the day's experience, to the slow, quiet work of sorting and storing and releasing. There is something about the event horizon that resonates with this, though gently and without forcing the comparison. A boundary beyond which no external information escapes. A region defined by what it holds within, rather than what it sends out. A space of internal process, sealed from observation. Not every enclosed thing is dark in a troubling way. Some enclosures are simply private, simply still. The galaxy that hosts TON 618 is itself an object of considerable scale. It has been classified as an elliptical galaxy, one of the rounder, more diffuse types, lacking the spiral arms of galaxies like our own Milky Way. Elliptical galaxies tend to be older, their star formation having largely concluded, their populations dominated by aging stars moving in relatively random orbits rather than the organized disk structure of younger spirals. The black hole at the center of such a galaxy maintains its gravitational influence across the entire structure, holding the galaxy together, the way the sun holds the planets in their paths, though at incomparably greater scales. The stars at the outskirts of the galaxy, moving in their wide, slow orbits, feel the pull of the central mass as a background condition of their existence, a steady, unchanging component of the space they inhabit. Not violent, not actively consuming, just present, as gravity is always present, shaping the paths things take through space. Researchers have found that the relationship between a galaxy's central black hole and the properties of the galaxy itself, its size, the velocity dispersion of its stars, the distribution of its mass, follows consistent patterns. More massive black holes tend to reside in more massive galaxies. The two seem to grow together, influence each other, co-evolve over billions of years in ways that are still being mapped. The black hole is not separate from the galaxy. It is in some sense the galaxy's center of gravity in both the physical and the organizational meaning of that phrase. Something that enormous, so deeply embedded in the structure of everything around it, becomes over time not a disruption, but an architecture. Not a force pulling things apart, but the thing that holds a particular arrangement of matter in its configuration. Scale at sufficient magnitude becomes foundation. The body at this hour has its own foundations operating quietly beneath awareness. The autonomic nervous system, the network of signals and responses that manages heart rate digestion, the dilation of blood vessels, the regulation of temperature, is running its slow background processes without any conscious direction. The breath continues without being told to. The heart maintains its rhythm. The muscles released from the demands of movement settle into their resting tone. The body is not passive in sleep or near sleep. It is active in a different register, performing without effort the maintenance that keeps everything running. Neuroscientists have observed that this background activity of the autonomic system is closely linked to the quality of rest that follows. When the autonomic nervous system is in a state of balance, when neither the activating nor the calming branch is dominant, the transition into sleep is smoother, deeper, more restorative. And one of the more reliable ways to support that balance, research indicates, is simply to allow the attention to rest on something that is stable, large, and non-threatening. Something that the threat detection systems find nothing to do with. The event horizon of TON 618, sitting quietly at the center of a distant galaxy more than 30 billion light-years away, is not a threat. It is an enormous, ancient, perfectly still object in a region of space you will never visit. It is, from the perspective of the body's alarm systems, completely irrelevant, and from the perspective of the part of the mind that finds rest in the presence of something vast and steady and permanent, it is perhaps exactly the right thing to be aware of at this hour. Something that will be there unchanged long after this night has ended, long after many nights have ended, long after everything immediate and pressing and requiring attention has run its course. Still sitting there, still massive, still in the most complete sense of the word, still. And there is still more to its story quietly waiting. The question of what happens to something this massive over the very long arcs of cosmic time, whether it continues to grow, whether it ever truly stops, what the universe's most ancient and most patient processes do to objects at this scale, that is a thread that runs deeper than the event horizon, deeper than the measurements that determined its mass, into a territory where physics and time intersect in ways that researchers are still exploring. That exploration moves at its own pace, unhurried, open-ended, following the evidence where it leads without needing to arrive anywhere in particular. The way perhaps this night is moving, one breath at a time, one quiet thought at a time, deeper in and further on. Growth in the universe is rarely a straight line. It moves in bursts and pauses, in long periods of stillness, interrupted by brief intervals of rapid change. In the way a glacier advances imperceptibly most of the time, then suddenly, when conditions align, covering ground that took centuries to approach. Or in the way certain trees grow slow in dry years, laying down thin rings, then wide and generous in wet ones, storing in their wood a record of every season they have survived. Growth across the natural world seems to prefer patience over urgency, to accumulate in the background quietly until conditions are right. The growth of ultramassive black holes follows something of this same principle. Not a continuous steady climb, but an episodic accumulation periods of intense activity when material is abundant and the feeding rate is high, separated by long stretches of relative quiet when the surrounding environment has been depleted and the engine idles. The extraordinary mass of Ton 618 was not assembled in a single, sustained effort. It was gathered in stages across immense spans of time through a process more patient than any human narrative can easily contain. The question of whether Ton 618 is still growing today, whether right now, in whatever present state it occupies material, is still falling inward and adding to its mass, is one that researchers approach with appropriate caution. What we observe of Ton 618 is its state from roughly 10 to 11% of the universe's current age. Whether it remains active now, whether its accretion disk is still luminous, whether it is still feeding at any significant rate, this is information that has not yet had time to reach us. The light-carrying news of its current state, if current state is even a meaningful phrase for something so remote, will not arrive for billions of years. It is in the most literal sense beyond knowing. What researchers can say, based on the broader pattern of how objects like Ton 618 evolve, is that most ultramassive black holes at the centers of large elliptical galaxies appear by the current era of the universe to have entered a significantly quieter phase. The dense gas clouds that fueled their early growth have largely been consumed or dispersed. The frequent galaxy mergers that delivered fresh material have become less common as the universe has expanded and its large-scale structure has grown more spread out. The conditions that allowed these objects to grow so large so quickly in the early universe have simply not persisted. This does not mean they are entirely still. Even a quiescent black hole continues to accumulate mass from stellar winds, from the occasional star that wanders too close and is disrupted from the slow accretion of whatever diffuse material remains in its vicinity. But the rate of growth researchers suggest is now orders of magnitude slower than during the peak activity that made these objects visible across billions of light years. If Ton 618 is growing today, it is growing the way a mountain grows genuinely, but at a pace so slow it would take geological instruments to detect. There is something in that image worth sitting with. An object that was once among the most energetically active things in the observable universe, now accreting at a rate so slow it barely registers. Not diminished exactly, not weakened, just arrived at a different phase. A phase defined not by output, but by presence, by the sheer patient fact of existing at that mass, in that location, holding that galaxy in its gravitational arrangement. The category of ultramassive black holes, those exceeding roughly 10 billion solar masses, contains, as far as researchers have been able to determine, a relatively small number of confirmed members. Finding and measuring objects this extreme requires a particular combination of circumstances. They must be either actively accreting, which makes them bright enough to detect at cosmological distances, or they must be close enough that their gravitational influence on surrounding stars can be directly measured. TON 618, at its extraordinary distance, was detectable because it is actively feeding when the light we receive left it. Other ultramassive black holes have been identified in nearby galaxies through the more painstaking method of tracking stellar motions near their centers, watching how stars move, and inferring from those motions the mass that must be holding them in those paths. One of the most massive black holes detected through this method resides at the center of a galaxy called NGC 1600, in a galaxy cluster not particularly distinguished by its surroundings, an ordinary patch of the cosmic web, remarkable only for what sits at its center. Its mass has been estimated at around 17 billion solar masses. Another candidate in the galaxy, known as Holm 15A, has been estimated at around 40 billion solar masses, making it among the largest black holes known in the relatively nearby universe. These objects are rare. They represent some extreme tale of a distribution, some outer limit of what the processes of galaxy formation and black hole growth have managed to produce in the observable universe. Researchers have noted that there may well be black holes more massive than TON 618 that have not yet been detected, either because they are no longer actively accreting and are therefore not producing the luminous signal that makes distant quasars visible, or because they reside in parts of the sky that have not been thoroughly surveyed, or because the instruments capable of detecting them have not yet been built. The census of the most extreme objects in the universe is, scientists are the first to acknowledge, still very incomplete. What is known is that these objects exist, that the universe in its early and most turbulent phase produced engines of extraordinary mass, and that those engines have been sitting quietly in some cases for billions of years at the centers of their galaxies, long after the noise and light of their formation has faded beyond detection. Patience in physics is not a virtue, it is simply a property, a description of how certain processes unfold relative to the human timescale, which is itself vanishingly brief by cosmic standards. But the word carries something useful anyway, because there is a quality to very long, slow processes that feels, when the mind approaches it at the right angle, genuinely restful. The deep time rhythms of geology, the multi-billion-year evolution of stars, the glacial accumulation of mass in an ultramassive black hole. These are processes that operate entirely outside the register of urgency. Nothing about them is rushing. Nothing needs to be completed by a particular moment. The timescales involved are so vast that the concepts of early and late, of ahead of schedule, or behind these simply do not apply. Psychologists who study the human relationship with time have found that the subjective experience of duration is closely tied to the pace of attention. When attention is rapid jumping between stimuli tracking many things simultaneously, time seems to compress. There is a feeling of not enough of rushing of the hours slipping past before they have been fully inhabited. But when attention slows, when it settles on something steady and unhurried, when it is not chasing anything or avoiding anything, time opens. The present moment becomes larger, more spacious. This is part of what happens in meditation, in quiet contemplation, in the particular quality of attention that attends the edge of sleep. The slowing of mental pace changes the felt sense of duration. And research suggests this slowing is not just subjective, it corresponds to measurable changes in brain activity, in the ratio of different frequencies present in the electroencephalogram, in the balance of neurotransmitters that regulate alertness and calm. When the mind is moving at the pace of deep time, not rushing toward the next thought, not pulling away from the current one, something settles. Something that was held without being noticed releases. There is a process in physics called Hawking radiation, proposed by the physicist Stephen Hawking in the 1970s, that describes a mechanism by which black holes can, over extraordinarily long periods, slowly lose mass. The process arises from the behavior of quantum fields near the event horizon. In quantum mechanics, the vacuum of space is not truly empty. It is filled with fluctuating fields that can briefly give rise to pairs of particles, one with positive energy and one with negative energy, which normally annihilate each other almost immediately. Near the event horizon of a black hole, the geometry of spacetime can cause these pairs to be separated, one particle falling inward, one escaping outward. The escaping particle carries away a small amount of energy, and over time, this process causes the black hole to very slowly radiate. The rate of this radiation is inversely related to mass. The more massive the black hole, the slower the evaporation. For a black hole, the mass of ton 618, the evaporation timescale is so incomprehensibly long that it makes the current age of the universe, 13.8 billion years, look brief by comparison. The evaporation time for an object of that mass would be measured in numbers so large they require scientific notation to express with exponents that dwarf anything encountered in ordinary physical calculations. Something in the range of 10 raised to the power of 100 years, or perhaps much longer. To say that this process is slow does not begin to capture it. It is slow the way the distance to ton 618 is far, in a register that the language of ordinary experience simply cannot reach. And yet the process theoretically continues, particle by particle, across a duration that has no human analogy, moving toward an endpoint that exists so far in the future that the stars will long since have burned out, the galaxies will have dispersed, and the universe will have entered a phase of such diffuse cool stillness that even the concept of change will have become almost theoretical. In that unimaginably distant future, if the theoretical physics is correct, TON 618, or rather whatever remains of it, will finally very quietly release the last of its energy and cease to be. Not with any drama, not with any announcement, Just a final infinitesimally small emission, and then nothing. Scientists sometimes find this thought not sad, but clarifying. That even the most massive thing the universe has yet produced is on the longest timescales temporary. That permanence, in the deepest sense, belongs not to any object, but to the laws that govern them. The laws that have been consistent from the first fraction of a second after the Big Bang to the unimaginable far future, those persist even as everything they describe eventually changes. The body resting now is engaged in its own slow processes, cells dividing and repairing in the quiet of the night, proteins being synthesized, memories being consolidated, the work of the day's experience being slowly integrated into the longer structure of a life. These processes are not dramatic, they are not visible, but researchers have found that they are profoundly sensitive to the quality of rest available to them, that what happens in the quiet hours, in the deep dark of sleep, is not simply absence of activity, but a different and essential kind of activity, one that cannot happen while attention is elsewhere, one that requires the conscious mind to step back, to lower its urgency, to stop directing, and simply allow. The deep time of the universe, the patient arcs of stellar evolution, the glacial accumulation of mass in ultramassive black holes, the vanishingly slow evaporation across timescales that dwarf the age of everything offers at this hour a particular kind of permission. Permission to exist at a pace that is not rushed, to inhabit a moment that does not need to become something else immediately. There is still further to go in this quiet drift through the territory of what gravity does to time itself. The strange and verified fact that near a mass like Ton 618 time does not pass the way it passes here. That the relationship between clock and duration is not fixed, but bends the way light bends, the way space bends in the presence of something very heavy. That layer of the story is close now, already beginning to take shape, the way shapes form at the edge of sleep, not forced, not summoned, simply arriving in their own time. Unhurried, as the deepest things always are. Time does not pass the same way everywhere. This is not a metaphor or a feeling or the subjective impression of someone having a particularly slow afternoon. It is a measured, verified, repeatedly confirmed fact about the physical universe, one of the stranger gifts that the physics of the last century has left us with. Time, it turns out, is not a fixed backdrop against which events unfold. It is itself part of the fabric of space-time, and like that fabric, it stretches and compresses in the presence of mass and velocity. Clocks run at different rates depending on where they are and how fast they are moving. The difference is usually too small to notice without instruments of extraordinary precision. But it is real, and it is always there. Albert Einstein's general theory of relativity, developed in the early part of the 20th century, predicted this effect, gravitational time dilation, as a consequence of the way mass curves space-time. The deeper you are in a gravitational well, the slower time runs relative to an observer further out. The closer you are to a massive object, the more pronounced the effect. At the surface of the Earth, clocks run very slightly slower than they do at high altitude. The difference amounts to a few microseconds per day, negligible in daily life, but significant enough that the satellite navigation systems orbiting the Earth must correct for it continuously. Without that correction, the accumulated time discrepancy would cause positioning errors that would grow to kilometers within hours. This is not a theoretical adjustment. It is a practical one built into the systems that guide aircraft and navigate ships and help a person find a particular street in an unfamiliar city. Gravitational time dilation is not abstract. It is operational. It runs in the background of modern life without most people ever knowing it is there. Near something like TON 618, the effect becomes far more extreme. As you approach the event horizon of a black hole, moving closer to a region of space-time so deeply curved that escape becomes impossible, the rate at which time passes for you, relative to an observer at a safe distance, begins to slow. Not as a sensation, not as a feeling of drowsiness or suspension, but as a genuine, measurable difference in the rate at which physical processes unfold. The oscillations of an atomic clock, the decay of a radioactive element, the firing of a neuron, the beating of a heart. All of these processes would proceed more slowly relative to an outside observer the closer they occurred to the event horizon. At the event horizon itself, from the perspective of an observer, sufficiently far away time for an infalling object would appear to slow to a stop. The object would seem to approach the boundary asymptotically, always getting closer, never quite crossing frozen in the last moment before the threshold. This is not an optical illusion. It is a consequence of the geometry of space-time at that boundary. The infalling object from its own perspective would cross the horizon in finite time. But the information about that crossing carried by light attempting to travel outward from the horizon would take infinitely long to reach the outside observer because it is moving through a region of space-time so severely curved that outward travel is no longer possible. Two perspectives, two genuinely different experiences of the same event, both described accurately by the same equations. Researchers have noted that gravitational time dilation is one of the aspects of general relativity that people find most difficult to absorb, not because the mathematics is impenetrable, but because it requires releasing the assumption that time is the same for everyone. That when we say it is midnight, the word midnight refers to something universal. It does not. It refers to the state of time at a particular location in a particular gravitational field. In another location, in a deeper or shallower gravitational well, midnight would arrive at a different rate, not differently named, differently experienced. The human brain, neuroscientists have found, has its own version of this flexibility with time. The subjective experience of duration is not a simple readout of an internal clock. It is a construction assembled from the rate of incoming information, the emotional state of the moment, the degree of attention being paid, and several other factors that interact in ways researchers are still mapping. Time feels different when you are frightened than when you are calm. It moves differently when you are deeply absorbed in something than when you are waiting for something. It contracts when experience is dense and expands when experience is sparse. Studies of people in extreme situations, moments of sudden danger for instance, have found that some individuals report a pronounced slowing of perceived time during the event, with experiences lasting fractions of a second, feeling, subjectively, like much longer intervals. Researchers have investigated whether this reflects an actual increase in the rate of information processing or a retrospective reconstruction. the dense encoding of many sensory details during a high alert moment, giving the memory of it a greater sense of duration than the clock would confirm. The evidence currently suggests the latter is more likely, but the phenomenon itself, the radical flexibility of experienced time, is consistent and real. At the other end of the spectrum, the approach to sleep is often accompanied by a different kind of temporal distortion. The interval between lying down and falling asleep can feel shorter or longer than the clock suggests, depending on the mental state. Deep relaxation tends to compress the felt sense of waiting. The mind, no longer tracking time, actively loses its grip on duration. Minutes pass without being registered as minutes. This is not a failure of the brain's timekeeping. It is in its own quiet way a form of time dilation, not gravitational, but attentional. The clock continues at its usual rate. The experience of its passage changes. There is a thought experiment that physicists sometimes use to approach the strangeness of time near a black hole. Imagine watching a clock fall toward the event horizon from a safe distance. As it approaches, you would see it ticking more and more slowly, the seconds between ticks growing longer, the light from the clock shifting toward longer wavelengths as it climbs out of the deepening gravitational well. Eventually, the clock would appear to nearly stop its ticking, slowing to an imperceptible crawl, its light red-shifted toward invisibility. It would seem to hang there, just above the horizon, for an effectively infinite time. Now imagine being the clock. From inside the falling reference frame, nothing unusual would be immediately apparent. The physics local to the clock, the behavior of matter and energy in its immediate vicinity, would continue normally. The clock would tick at its usual rate, the horizon would approach and be crossed. Time felt from within would not slow. The strangeness of the situation is entirely a matter of perspective, of the relationship between two reference frames in radically different regions of curved space-time. This thought experiment quietly dismantles a number of assumptions. The assumption that slowness and speed are absolute rather than relational. The assumption that an observer outside a situation has privileged access to what is really happening inside it. The assumption that time is something experienced the same way by everyone, regardless of where they are or how they are moving through the geometry of space. Scientists suggest these are not merely abstract philosophical revisions. They are descriptions of a universe that genuinely operates this way. The relativity of time is not a quirk or a special case. It is woven into the structure of reality, operating at every scale, from the navigation satellites correcting their clocks above the Earth to the extreme time dilation near the event horizon of an object as massive as Ton 618. The body at rest has its own slow rhythms that the waking mind tends to override. The respiratory rate during deep relaxation falls below the typical waking rate. The heart slows. The electrical activity of the brain shifts toward lower frequencies, from the beta waves associated with active alert thinking toward the alpha waves of relaxed wakefulness, and then deeper in, toward the theta waves that characterize the earliest stages of sleep. Each of these transitions represents a genuine change in the physical state of the brain, a different pattern of activity, a different relationship between the systems that generate experience. Researchers who study sleep onset have found that this transition is not a single threshold, but a gradual process, a slow drift through a continuum of states, each one slightly quieter than the last. The boundaries between wakefulness and sleep, when examined closely, turn out to be softer and less clearly defined than they appear in everyday experience. There is no precise moment when sleep begins. There is a gradual releasing of muscle tone, of sensory responsiveness, of the continuous self-monitoring that characterizes full wakefulness until the system has crossed by imperceptible degrees into a different mode altogether. This process, allowed to unfold without interference, tends to produce the deepest and most restorative sleep. The stages reached most easily, when the transition is slow and unforced, are the stages associated with the consolidation of memory, the repair of cellular damage, the regulation of hormonal systems that manage stress and immune function. The body uses the quiet of the night for work that the day does not allow, and the quality of that work depends in part on the quality of the transition, on how gently and completely the waking mind releases its hold. At this hour, that releasing may already be underway. The voice you are following is not urgent. The ideas it carries are not demanding. The pace at which they arrive is not faster than the breath. And the breath, if you attend to it for a moment without trying to change it, may already be slower than it was an hour ago. Near the event horizon of TON 618 time dilates by factors that dwarf any human measurement. Clocks near that boundary would run at rates so different from clocks here that the relationship between the two would be in any practical sense incomparable. An hour there could correspond to a duration here that exceeds the current age of the universe. A duration there that corresponds to a human lifetime here might be, from the outside, barely a flicker. The extreme warping of time near such an object is not accessible to any human experience. It cannot be visited, felt, or directly confirmed. It exists in the mathematics verified through the consistency of the theory that predicts it, with observations of much smaller time dilation effects closer to home. It is extrapolated from what is known, extended to a scale where the extrapolation becomes almost surreal. And yet, the underlying principle, the bending of time by mass, is not exotic. It is operating right now everywhere. The person at sea level ages infinitesimally faster than the person on a mountaintop, and that person ages infinitesimally faster than the satellite in orbit. These are real differences in the accumulation of time. Measured, confirmed, built into the devices we carry in our pockets. TON 618 is just the extreme end of a continuum that includes the Earth, the Sun, every planet and star and wandering rock in the universe. Mass warps time everywhere it exists, and where mass is greatest, that warping becomes the most profound, the most strange, the most removed from ordinary experience, the most quiet in its way. Because at the extreme edge of time dilation, where time slows towards stillness, there is something that resembles, without being, rest. Not the rest of sleep, which is active and purposeful, but the rest of a clock that has nearly stopped, of a system approaching its own edge, of something enormous, old and still. The connection between the body's slow rhythms and the deep time rhythms of the universe is not symbolic, not a literary device. It is, in a modest and grounded sense, a real one. The atoms in the body were forged in stellar interiors. The calcium in bone, the iron in blood, the oxygen drawn into the lungs. With every breath, these were produced in nuclear reactions inside stars that lived and died before the sun was born. The body is, in the most literal way available to physics, made of ancient cosmic material. The rhythms that regulate it, the circadian cycles, the tidal influences on biological processes, the deep connection between organism and the slow rotations of the world are embedded in a universe that has been running its own rhythms for billions of years. Resting here, at this hour, in this particular arrangement of matter that has been organized briefly into the shape of a life, there is something that belongs to that larger continuity, something that was never separate from it, something that in the quiet of the night needs no particular effort to remember. It simply is. As Ton 618 simply is. As time simply is moving at different rates in different places, none of them wrong, all of them equally part of the same unfolding. And from here, the drift continues into the territory of what it means for something this vast to exist in silence, without witnesses, without acknowledgement, in the deep and permanent privacy of a universe that holds its most extreme creations at distances where they can barely be heard. That silence has its own quality, its own texture, and it is already beginning to take shape just ahead in the soft dark of what comes next. Space is not empty. This is one of those facts that sounds simple, and then the longer you hold it, reveals itself to be anything but. The intuition that space, the vast distances between stars, between galaxies, between clusters of galaxies, is essentially nothing, just absence, just the void through which things travel, turns out to be incorrect in ways that matter deeply to how the universe works. Between the stars, there is gas, diffuse extraordinarily thin by any earthly standard, but present hydrogen atoms drifting singly or in pairs, occasional molecules of water and carbon monoxide, and ammonia dust grains composed of silicates and carbon compounds, all of it moving in slow, vast currents shaped by the gravitational architecture of the galaxy. Between galaxies, the intergalactic medium is thinner, still closer to a true vacuum than almost anything that can be produced in a laboratory on Earth, but not quite empty. Strands of warm, ionized gas thread through the spaces between galaxy clusters, tracing the large-scale structure of the cosmic web. Even between galaxy clusters in the deepest voids of the universe, there are stray particles, faint radiation fields, the omnipresent hum of the cosmic microwave background, spreading through all of space, equally in every direction, a remnant warmth from the universe's earliest moments. The universe, in other words, is full, not crowded, nothing like crowded, but threaded through with connection in every direction, at every scale, in forms too diffuse to see, but present enough to measure. This connectedness has a particular relevance to black holes and the galaxies that surround them. For a long time, astronomers thought of a supermassive black hole as something essentially isolated within its galaxy, a gravitational center certainly, but otherwise passive, contained sealed behind its event horizon and affecting only the stars and gas in its immediate vicinity. What has emerged from decades of closer observation is a picture considerably more dynamic and more interconnected than that. The feedback between a central black hole and its host galaxy turns out to be one of the more important relationships in galaxy evolution. When a black hole is actively accreting, when the quasar phase is underway, the energy it releases is not simply radiated away into space. It interacts with the surrounding gas. It heats it, pushes it outward, can in some cases drive powerful winds that sweep through the entire galaxy, removing the raw material for star formation, effectively regulating the rate at which the galaxy grows. Researchers have found evidence that galaxies containing more massive black holes tend to have older stellar populations, collections of stars that formed earlier and stopped forming sooner, as if the central engine had intervened in the process. The black hole's influence channeled through its outflows and radiation appears to have helped set the pace of the galaxy's development. Not simply a passenger in the galactic structure, but a participant, a regulator, something whose presence shaped the history of every star that formed around it. This kind of relationship between a central massive object and the distributed system surrounding it appears at many scales in the natural world. The way a keystone species shapes the ecology of an entire environment without necessarily being the most visible or abundant member. The way certain quiet structures in a complex system exercise an influence far beyond what their immediate footprint would suggest. Presence does not always announce itself. Influence does not require visibility. Silence in physics is not the absence of information. It is a particular condition in which information is not being transmitted outward or not in forms that reach a given observer. The interior of a black hole is, from an outside perspective, perfectly silent in this sense. No signal, no particle, no form of radiation can carry information from within the event horizon to the space outside. Whatever processes occur inside, and physicists have speculated at length about what those processes might be, none of them can communicate their occurrence to any external observer. The interior is informationally isolated, not simply quiet, but sealed. This has led to one of the more philosophically interesting puzzles in modern theoretical physics, the information paradox. In quantum mechanics, information is conserved. The complete description of a physical system at one moment in time should, in principle, allow the complete description at any other moment to be derived. Information does not simply vanish. It transforms, encodes itself in different forms, disperses, but does not disappear. And yet, a black hole seems to violate this principle. Matter and energy fall in carrying information about their states. The event horizon seals behind them. The black hole, through Hawking radiation, eventually evaporates, but the radiation it emits appears to be thermal, essentially random, carrying no specific information about what fell in. The original information seems to be lost. Whether it truly is lost, whether the universe contains a genuine exception to quantum mechanical information conservation, or whether the information is somehow preserved in subtle correlations in the Hawking radiation that current theory cannot yet describe, is a question that some of the most careful thinkers in theoretical physics have spent decades working on. Stephen Hawking himself revised his position on the question more than once over the course of his career. The current state of understanding is that most physicists believe information is preserved in some way, but the precise mechanism remains an open and genuinely difficult problem. It seems that the universe, at its most extreme, asks questions that its own laws have not yet finished answering. The human experience of silence has its own depth that changes with attention. In an environment without external sound, a situation rare enough in modern life to be actively sought out by those who find it restorative. The first thing most people notice is that silence is not the absence of sound, but a different quality of it. The body generates its own acoustic environment. The pulse can become audible. The sound of air moving in the lungs is present. The subtle tinnitus that almost everyone carries to some degree becomes more prominent. And beneath all of this, something that is not quite sound, but is registered through the same system, a felt resonance, a sense of the space around the body, the particular acoustic character of a room or a night. Researchers who study auditory neuroscience have found that the brain does not simply process silence as an absence of signal. In quiet conditions, the auditory cortex continues to be active, maintaining its readiness, attending to subtler and subtler gradations of the sonic environment. The threshold for detection lowers. The system becomes more sensitive. Things that would be filtered out in a noisier environment begin to register. This heightened sensitivity in quiet conditions has been associated in some research with a broader shift in cognitive processing, a move toward more internal, more contemplative modes of thought. The brain, with less external input to track, turns some of its processing capacity inward. Memories surface more readily. Associations form more freely. The connections between ideas that the busy mind tends to pass over in favor of more immediate concerns become more available. Psychologists sometimes describe this as a state of productive quiet, not the vacant quiet of boredom, but the full quiet of deep rest combined with gentle, unforced mental activity. It is associated with some of the moments people later describe as genuinely clarifying. Not because they were trying to solve anything, but because they were not, and something settled on its own. The universe's silence, the profound absence of communication from behind an event horizon, from the interior of a region sealed against information exchange, is of a different order entirely. But the quality it evokes, approached from a sufficient distance, through the medium of a quiet night, and a mind already beginning to slow, is not so different in feel from the silence of a room gone still, of a world grown temporarily quiet around a single resting body. Both are in their way whole. The large-scale structure of the universe, the cosmic web as astronomers call it, is one of the more quietly astonishing features of the cosmos when seen at sufficient scale. Galaxies are not distributed randomly through space. They cluster along filaments, vast thread-like structures of dark matter and gas that stretch across hundreds of millions of light-years, with galaxy clusters concentrated at the nodes where filaments intersect, and enormous voids occupying the spaces between. The pattern, when mapped in 3 dimensions using the positions of millions of galaxies, resembles nothing so much as a biological structure. The branching networks of neurons in a brain, or the mycelial networks of fungi spreading through soil, or the vascular systems of large organisms. Similar patterns arising at radically different scales through radically different physical processes. Researchers are careful not to overstate the comparison. The resemblance is structural, not causal. The cosmic web and the neural network of a brain are produced by different mechanisms and operate according to different principles. But the similarity in pattern, the nodes, the filaments, the voids, the hierarchical clustering has prompted genuine scientific reflection on what it means for similar structures to emerge independently at such different scales. It may be that certain geometries arise naturally from any system in which things attract each other, cluster, and leave gaps in between. That the pattern is not specific to neurons or fungi or galaxies, but is the natural outcome of any sufficiently large network of interacting objects that follow a consistent set of rules. A pattern written into the logic of connection itself, appearing wherever that logic operates freely enough to leave its mark. TON 618 sits at a node of this structure, a point where the filaments of the cosmic web converge, where the density was sufficient to support the formation of an extraordinarily massive galaxy, and at its center, an extraordinarily massive black hole. Its existence is not accidental. It is the product of a particular location in the cosmic web, a location of confluence, of accumulated density, of the kind of sustained environmental richness that allows the most extreme outcomes to occur. Place, it turns out, matters, even at cosmological scales, even across billions of light years. Where something is located in the structure of the universe shapes what it becomes. The body carries its own structural history in ways that neuroscience has only recently begun to map in detail. The connections between neurons, the synaptic architecture of the brain, are shaped by everything the brain has experienced. Every repeated thought, every practiced skill, every emotional pattern encountered and navigated, every piece of information attended to and incorporated, all of these leave physical traces in the connectivity of the neural network. The brain is not a fixed structure that passively receives experience. It is a structure that experience actively shapes continuously throughout a lifetime. Researchers call this property neuroplasticity, and while it is more pronounced in early development, it continues in a quieter form for as long as the brain remains active. The connections formed during the day, the associations made, the information processed, the emotional experiences navigated, are consolidated and integrated during sleep. The sleeping brain reviews, prunes, strengthens, and reorganizes its own architecture. This is not a metaphor for learning. It is the literal mechanism by which learning becomes permanent. The neurons that fire together during waking experience are during the sleep that follows, engaged in the work of deciding what to keep, what to release, what to bind more tightly into the network. At this hour, that process is either underway or very nearly beginning. The connections that will be strengthened by this night's sleep are already determined by this day's experience. The brain, in its quiet and diligent way, is preparing to do its most essential work. What it needs from the conscious mind at this point is simply this release, the loosening of directed attention, the allowing of the system to operate according to its own deep intelligence, without interference, without agenda, without the pressure of a mind that is still trying to be somewhere, or do something, or understand something before the night is over. There is nothing that needs to be understood before sleep. There is nothing that requires completion tonight. The universe has been doing its work for 13.8 billion years without requiring anything of you. Ton 618 has been sitting in its distant silence for most of that time, holding its mass, shaping its galaxy, contributing its presence to the cosmic web without needing to be witnessed or acknowledged or comprehended. And you, in your particular location, in this same universe, in this particular arrangement of atoms that has been conscious for a brief and remarkable interval, you are also simply here, simply present, simply part of the same ongoing thing. The cosmic web connects everything to everything else in the end, not through any mystical mechanism, but through the ordinary physics of gravity and the expansion of space, which has been distributing matter and shaping structure since the first fraction of a second after the beginning. Every massive object affects every other massive object, however slightly. Every photon that has ever been emitted contributes to the radiation field of the universe. Every piece of matter that has ever existed has left its trace on the space-time through which all subsequent matter moves. Nothing is truly isolated. Not even the most sealed interior of an event horizon is disconnected from the universe outside. It still bends. Space-time still draws matter toward it, still participates in the gravitational conversation that holds the cosmos in its current arrangement. And this room, this body, this particular and temporary arrangement of the universe's matter, listening to these ideas at this particular hour, it is connected to all of that as well. Not in a way that demands anything, not in a way that imposes any weight, just in the quiet, physical, unremarkable way that everything is connected to everything else through the medium of space-time, through the long, slow influence of gravity, through the light that crosses the distance between things and carries in its stretched and patient arrival the news of what exists. The last layer of this journey is close now, the one where the distance between there and here dissolves not dramatically, but the way fog dissolves in the morning so gradually that there is no single moment when it is gone, only the slow realization that the air has changed, that everything has grown quieter, that there is nothing left to reach for. Only this, only now, only the breath and the dark and the vast, unhurried continuity of a universe that has been all along exactly where it is. Somewhere between waking and sleep, the mind does something it rarely does during the day. It lets go of the story it has been telling about itself. The continuous narration, the quiet internal voice that tracks what needs to be done, what was said, what might happen, what is expected, that voice begins to soften. Not because it has been silenced, but because the conditions that require it are no longer present. The body is still. The room is dark. The day has passed into the past, where it can wait. And without the constant input of a world requiring navigation, the narrator simply has less to say. Neuroscientists have observed that this loosening of self-referential thought is one of the more distinctive features of the transition towards sleep. The network of brain regions associated with the ongoing construction of a sense of self, sometimes called the default mode network, gradually reduces its activity during sleep onset. Not all at once and not completely, but the grip of it softens. The story of you becomes for a few hours less insistent, and in that softening, something else becomes available. Something quieter. Something that was always there beneath the narration, simply waiting for a pause. The universe does not narrate itself. This is worth sitting with very gently for a moment. The processes that govern it, the expansion of space, the slow orbital motions of galaxies around each other, the accumulation of mass in the deep centers of galactic nuclei, the long patient cooling of a cosmos that has been running down its initial heat for nearly 14 billion years. None of these processes involve anything like commentary. They simply proceed. Consistently, continuously, according to the same physical laws that have operated without revision since the first moments after the beginning. TON 618 does not know it is massive. The event horizon does not mark its own boundary. The light that left that region billions of years ago did not intend to travel. It simply moved the way light always moves, following the geometry of the space it inhabited, carrying information without meaning to arriving here without purpose, and being received by minds that evolved the capacity to find meaning in things that contain none, as something that feels in the dark of a quiet night, almost like a message. Scientists suggest that this meaning-making is one of the most fundamental and most deeply human of cognitive processes. The brain researchers have found is pattern recognition machinery operating at extraordinary efficiency. It finds faces in clouds, narratives in sequences of random events, significance in coincidences. It cannot quite help itself. Meaning is not found so much as produced by the encounter between a world that simply is and a mind that is constitutionally inclined to ask what it means. There is nothing wrong with that. It may be exactly right. The universe may require witnesses to complete something about itself that the laws of physics alone cannot provide. Or it may not require anything at all, and the witnessing may be its own sufficient reason. Either way, here you are, witnessing, and it is enough. The body is extraordinarily good at knowing when to release. Not always in waking life, where habit and anxiety and the accumulated tensions of moving through a demanding world keep the muscles slightly braced, the breath slightly shallow, the jaw slightly held. But given the right conditions, warmth, stillness, darkness, the gradual departure of urgency, the body's intelligence asserts itself. The parasympathetic nervous system, which governs the restorative functions, begins to take precedence over the sympathetic system that manages alertness and response. Heart rate continues its slow descent. Breath deepens and spaces out. The small muscles around the eyes soften. The hands, if you notice them now, may already be more open than they were an hour ago. Researchers have found that the physical relaxation of the body and the mental relaxation of directed thought tend to move together, each one facilitating the other in a kind of mutual releasing. When the body releases physical tension, the mind tends to follow. When the mind stops insisting on maintaining vigilance, the body takes that as permission to settle further. The two systems often pulling against each other during the demands of waking life find in the right conditions a natural alignment. This is what rest actually is, in physiological terms. Not simply the absence of activity, but the presence of a different kind of activity, the coordinated cooperative unwinding of systems that have been held ready all day. A returning, a coming back to some baseline state that the body knows intimately, has returned to thousands of times, and knows exactly how to reach. It is already underway. The light from the most distant objects in the observable universe has been traveling since long before the Earth existed, and it is still arriving. Right now, at this precise moment, photons that began their journey in the early universe are completing it, striking the surfaces of telescopes, entering the apertures of instruments, being converted into data that human beings will eventually sit with and try to understand. The universe is continuously delivering its past to the present. The two are not as separate as they seem. The past is not behind us, sealed off, inaccessible. It is arriving in light constantly, updating our instruments with news that is billions of years old and entirely new at the same moment. What this means in the quietest possible terms is that distance and time and the processes of the universe are not set against us. They are simply doing what they do, expanding, cooling, delivering ancient light to patient instruments, moving as they have always moved, without urgency, without error, without anything resembling the pressure that the human mind generates when it insists that things should be different from how they are. The universe does not insist. It simply proceeds. And in the long, slow journey of a photon from TON 618 across the expanding space of 33 billion light-years, through the darkness between galaxy clusters, through the vast and nearly empty intergalactic medium, through the local group, through the small bubble of space our galaxy occupies, through the solar system, through the thin atmosphere of this planet, into the waiting eye of a telescope. Somewhere on a mountain top, there is a kind of patience that has no human equivalent. Only the faintest echo of it exists, perhaps in the quality of a night like this one, when there is nowhere to be and nothing required, and the breath simply continues as it has always continued, without needing to be told. Sleep, researchers have found, is the condition in which the brain clears itself. During waking hours, the activity of neurons produces metabolic waste, byproducts of the chemical processes that power thought and perception and response. These accumulate in the fluids surrounding the brain's cells throughout the day. And during sleep, a system of channels in the brain, sometimes called the glymphatic system, becomes significantly more active, flushing this accumulated waste out, clearing the neural environment in preparation for the next day's activity. The sleeping brain is, in this very literal sense, a brain engaged in renewal, in making space, in removing what has built up and restoring the conditions that allow clear, fresh function. This process cannot happen, or cannot happen nearly as well, while the brain is occupied with the demands of consciousness. It requires the step back, the release of directed awareness, the long, dark interval in which the maintenance crew can do their quiet work. There is nothing passive about sleep, despite how it feels from inside. It is one of the most actively restorative processes the body undertakes, and the quality of what happens during it depends in part on how completely the transition into it is allowed to proceed, on how fully the waking mind is willing to hand over to the processes that do not require its supervision. You do not need to supervise anything tonight. The body knows what to do. It has always known. Long before you learned to think about it, the body was doing this clearing, restoring, renewing in the dark. And it will do it again, tonight, with the same quiet competence it has always brought to the work. The stars that are visible from Earth on a clear night, the ones close enough and bright enough to register as individual points of light, rather than the collective glow of a distant galaxy, are all within our own Milky Way. The nearest of them, a small, faint star in the southern constellation Centaurus, is about 4 light-years away. Light from it takes 4 years to reach us. The furthest objects visible to the unaided human eye under the best conditions are the Andromeda and Triangulum galaxies at approximately 2.5 million and 3 million light-years respectively. On an exceptionally clear night away from city lights, they can be seen as faint, slightly smudged points or as a soft glow on the edge of visibility. When you look at the Andromeda galaxy, the light entering your eye left that galaxy more than 2 million years ago, long before anatomically modern humans existed on this planet. TON 618 is thousands of times further still, so far that the light from it is not visible to any unaided eye, not detectable without the most sensitive instruments, not accessible to direct experience in any ordinary way. And yet, it is real. It is there in whatever state it currently occupies, doing whatever it currently does, holding its mass and its silence in a region of space that the expanding universe has placed beyond our reach in every practical sense. The fact that it exists, the fact that the universe contains objects at that scale, at those distances, in those ancient configurations, does not demand anything of you. It does not require contemplation or response or any particular feeling. It is simply part of what is true about the place you inhabit, a true thing, sitting quietly in the dark, at an almost unimaginable distance from here. The breath is slower now, perhaps, than it was when this began. The body heavier in the comfortable way that heaviness comes when the muscles finally agree to stop holding. The mind looser, less insistent on tracking where each thought leads. The boundary between what is heard and what is simply felt has probably blurred somewhat by now. These are not things to assess or correct. They are what happens when the conditions are right and nothing is in the way. The universe has been cooling since the first moment of its existence, moving in its long and patient arc from a state of concentrated blazy energy towards something more diffuse, more spread out, more evenly distributed across the expanding space it inhabits. Cosmologists call this the increase of entropy, the gradual movement of any system toward its lowest energy state, its most probable configuration, its natural resting place. It is happening at every scale, in every direction, without hurry. Stars cooling into white dwarfs, galaxies aging from blue and bright to red and quiet. The cosmic microwave background growing fainter as the universe expands and its temperature falls. Everything on its own timescale, finding its way towards stillness. This night is part of that. This room is part of that. This breath, this particular interval of quiet between one moment and the next, part of the same long, unhurried movement of a universe that has been moving toward rest since long before there was anyone here to notice. You have traveled a long way tonight, not in any direction that a map could show, but in the way the mind travels, following a thread moving through layers of a thing, arriving somewhere different from where it started, without quite being able to say when the change happened. From a dark room to an even darker region of space, from the scale of a breath to the scale of something 66 billion times the mass of the sun, from the speed of a thought to the speed of light, and then to the patience of light crossing distances that dwarf anything the human experience has prepared us for. And now, gently back, not with effort, not as a task, just the natural return that happens when a mind has gone as far as it needs to go and finds at the end of the traveling that it is still exactly where it started, in a body, in a room, in a night that is doing what nights do, holding the small hours with the same indifference and the same quiet hospitality it has always extended to the sleepless and the drifting and the ones who needed for a little while to think about something much larger than themselves. The atoms in this body were forged in stars. This is still true. It will still be true in the morning and the morning after that. And the light from TON 618 is still arriving somewhere right now at this very moment, falling on instruments that cannot fully see what they are receiving, carrying news from a past the universe has long since moved through, patient and undiminished by the distance. Some things travel a very long way to arrive, and some arrivals need no announcement. They simply happen, quietly, in the dark.